Hello there and welcome to Physics with William, where curiosity gets comfortable, complicated ideas loosen their ties, and the universe is allowed to explain itself at a pace that does not require anyone to rush. Tonight, we are going to spend some quiet time with an object that seems simple enough to fit in your hand. Stick to a refrigerator, hold up a shopping list, or mysteriously collect every paperclip in the drawer. A magnet does not look especially rebellious. It usually sits there without making a fuss. It does not glow, hum, or demand to be admired. And yet, if you try to divide it in what seems like the most obvious way, it refuses to behave as expected. Cut a wooden ruler in half, and you have two shorter rulers. Cut a piece of string in half, and you have two pieces of string. Cut a sandwich in half, and depending on how generous you are feeling, you may have lunch for two. But cut a magnet in half, and something much stranger happens. You do not get one piece with the North Pole and another piece with the South Pole. Instead, you get two smaller magnets, and each one has a North Pole and a South Pole of its own. That simple fact is easy to demonstrate and surprisingly difficult to stop thinking about once you notice it. It is as though the magnet carries a rule inside itself, a rule saying that North and South must travel together. You can shorten the magnet, chip it, grind it, or break it into smaller and smaller fragments, but the partnership remains. Every fragment develops the same basic arrangement. One end behaves like North, the other behaves like South, and the invisible magnetic field continues looping around it as if nothing particularly dramatic has happened. The magnet does not care that you are trying to separate its two personalities. It simply reorganizes and carries on, which is more emotional resilience than many of us manage before breakfast. Perhaps you have tried this experiment yourself, or perhaps you have only seen it in a classroom demonstration. A teacher holds up a bar magnet, marks the ends, and then explains that cutting it will not isolate the poles. It sounds almost like a trick. Surely if one end is north and the other is south, then slicing through the middle should separate them. That is how ordinary objects work. A loaf has a left end and a right end. Remove one end and it remains removed. A road has two directions. Stand at one point and you can choose one without bringing the other along. Magnets seem to ignore that common sense. Their poles are not separate attachments placed at opposite ends. They are not like caps on a bottle that can be unscrewed and placed on different shelves. The poles are expressions of the whole magnetic structure, and when the structure is divided, each new piece forms a complete magnetic pattern. Before we go any farther, let me ask you something gently. Where are you listening from tonight, and is there a magnet somewhere nearby? Perhaps one is holding a note to your fridge. Perhaps there is one hidden inside your headphones, your phone, a cupboard latch, a speaker, a motor, or the small charging cable that seems able to find the floor with remarkable efficiency. Magnets are woven so deeply into modern life that we often stop noticing them. They help convert electricity into motion, motion into electricity, sound into electrical signals, and electrical signals back into sound. They guide compasses, spin motors, store information, secure doors, move trains, and sit quietly inside machines that would be useless without them. Yet the question we are asking tonight does not begin with a giant laboratory or an expensive machine. It begins with a small solid object and a very ordinary pair of scissors, a saw, or perhaps a regrettable attempt involving a brittle classroom magnet. If you find this kind of slow scientific wandering soothing, interesting, or simply helpful at the end of a long day, you might gently tap the like button and subscribe to Physics with William. It helps this quiet corner of science reach other curious minds who may also enjoy learning why the universe behaves strangely, while they're trying not to stay awake too long. There is no need to take notes, memorize terms, or sit up with the determined expression of someone preparing for an exam. You can simply listen. Let the ideas arrive one at a time, and should you drift off somewhere between magnetic poles and moving electrons, the magnet will still be here tomorrow, stubbornly keeping North and South together. The puzzle becomes especially interesting because magnets make their poles seem so local. Hold two bar magnets near one another, and you can feel the difference between their ends. One pair pulls together, another pair pushes apart. Turn one magnet around and the behavior reverses. The force is strong enough to feel directly, even though nothing visible stretches between the objects. There is no string, no hook, no puff of air, just an invisible field reaching through the space between them. Since the effect appears strongest at the ends, it is natural to imagine that the North Pole lives at one end and the South Pole lives at the other, almost like two different substances stored inside the same object. If that picture were correct, cutting through the middle ought to work. One piece should keep the north substance, and the other should keep the south substance. But nature does not arrange ordinary magnets that way. Instead, magnetism comes from activity happening throughout the material. Deep inside a magnet, enormous numbers of atoms contribute tiny magnetic effects. Those effects are connected to electrons, which possess properties that allow them to behave in a limited but useful sense like microscopic magnets. In many materials, these tiny magnetic influences point in different directions and mostly cancel one another. The object contains magnetic ingredients, but they are arranged like a crowd of people all trying to leave through different doors. The result is very little overall movement in any one direction. In a permanent magnet, however, many of those tiny contributions become organized. Large groups of atoms line up their magnetic behavior, creating regions that reinforce one another. When enough of the material becomes aligned, the whole object produces a strong field. This means the north and south poles are not two separate ingredients. They are the two ends of a continuous pattern created by the alignment inside the magnet. Imagine a long line of tiny compass needles, each pointing in roughly the same direction. The line has one orientation at one end and the opposite orientation at the other, but you cannot cut the line and obtain a piece with only the front ends of the needles and another piece with only the back ends. Each needle already has both ends. Divide the line and you create two shorter lines, each with the same basic structure. That image is not a complete description of what is happening inside a real magnet, but it gives us the shape of the answer. The magnet does not contain a north half and a south half. It contains countless tiny magnetic contributions arranged together, and the poles emerge from the way the entire collection is organized. Even that explanation raises another question. If the tiny building blocks behave like magnets, why can we not keep cutting until we reach one that finally separates? This is where the mystery deepens. The magnetic behavior associated with electrons is not caused by little physical arrows spinning like toy tops inside the atom. The word spin is used in physics, but it does not mean that an electron is literally a tiny ball turning around in space. It is a quantum property, something fundamental that gives the electron a built-in magnetic character. Electrons also move within atoms, and that motion contributes to magnetism as well. In certain elements, especially iron, cobalt and nickel, the arrangement of electrons allows neighbouring atoms to influence one another in a way that encourages magnetic alignment. The result is not merely a collection of separate miniature bar magnets, but a quantum organised state spread through parts of the material. So when a magnet is broken, you are not slicing a simple line between north and south. You're interrupting an organised material. At the new broken surfaces, the internal arrangement continues, and each fragment establishes its own complete field. The place where the cut was made becomes a new pair of ends. One side of one fragment behaves as a new pole, while the corresponding side of the other fragment behaves as the opposite pole. The magnetic field adjusts around both pieces. Nothing needs to travel rapidly from the old ends to the new ones like workers rushing to fill vacant positions. The new pole behavior appears because a boundary has been created in a material whose magnetic order was already present throughout it. It may help to think about a row of arrows painted on a long strip of paper. Every arrow points the same way. At the beginning of the strip, you see the tails of the arrows. At the far end, you see the arrowheads. Now cut the strip in the middle. The left piece still has tails at one end and arrowheads at the other. The right piece does too. You have not created a fragment made only of arrowheads or only of tails, because each arrow was complete before the cut. A real magnet is more complicated, and its internal structure is not a neat row of painted arrows, but the reason cutting fails is similar. The polarity belongs to a pattern that repeats through the material, not to two detachable reservoirs sitting at the ends. This is also why the phrase cutting a magnet in half can be slightly misleading. Physically, you certainly can cut or break many magnets, although some are brittle and may shatter with enthusiasm. What you cannot do is cut the magnetic dipole into isolated ordinary poles. A dipole is simply a paired arrangement with two opposite aspects. Every familiar permanent magnet is a magnetic dipole. The word tells us that there are two poles, but it also hints that they belong to one structure. Divide the structure and you create smaller dipoles. Continue dividing and the same principle remains, until the material becomes so small that other complications appear, including changes in how stable the magnetic alignment can be. But the ordinary process never leaves you holding a free north pole in one hand and a free south pole in the other. That may sound like nature has forbidden single magnetic poles entirely, but physics is rarely kind enough to make the story quite so tidy. Scientists have spent a great deal of time searching for particles or objects that would behave as isolated magnetic poles. These hypothetical objects are called magnetic monopoles. A monopole would be something like a north pole without a south pole attached, or a south pole without a north. Some theories in particle physics suggest that such objects could exist. Certain ideas about the early universe even imply that they may once have been produced under conditions far more extreme than anything we encounter today. Experiments have searched for them in cosmic rays, ancient materials, particle collisions, and sensitive detectors. So far, no confirmed fundamental magnetic monopole has been found. There are also systems in certain specially arranged materials where disturbances can behave as if they were magnetic monopoles. These are not isolated fundamental poles in the same sense that theorists imagine. They are collective effects emerging from the behaviour of many atoms. They are a little like a gap moving through a crowded theatre. The gap can behave as though it is an object with its own position and motion, even though what really moves are people changing seats. Physicists can study these monopole-like excitations and learn a great deal from them, but they do not allow someone to cut a refrigerator magnet and finally obtain a lonely North Pole looking for somewhere to go. The refusal of magnets to split into separate poles also connects to the shape of magnetic fields. Magnetic field lines around an ordinary magnet form closed loops. Outside the magnet, we describe them as emerging from the North Pole and curving toward the South Pole. Inside the magnet, the pattern continues back toward the north. The lines do not simply begin and end in empty space. They loop. This does not mean that literal threads are wrapped around the magnet. Field lines are a way of drawing the direction and strength of the magnetic field. But the looping pattern captures something important. Magnetism, as we observe it in ordinary matter, has no isolated source or sink where the field begins or disappears. The field forms a continuous structure. Electric fields behave differently. Positive and negative electric charges can exist separately. An electron carries negative electric charge. A proton carries positive electric charge. You can have more of one charge than the other in a region, and electric field lines can begin on positive charge and end on negative charge. This makes the magnetic case even more puzzling. Electricity and magnetism are deeply connected. They are parts of one electromagnetic framework. Moving electric charges create magnetic fields, and changing magnetic fields can create electric effects. Yet electric charge appears in isolated positive and negative units, while magnetic poles, in ordinary experience, appear only in pairs. Why should the universe allow a single electric charge but apparently insist that magnetism arrive with both ends included? That question reaches beyond the magnet on the fridge. It leads toward the structure of electromagnetism, the behaviour of quantum particles, the internal order of materials, and some of the most ambitious theories in modern physics. A small magnet becomes a doorway into a much larger subject. It invites us to ask where magnetic fields come from, why some materials remember a magnetic direction while others do not, how electrons cooperate across a solid object, and whether a truly isolated magnetic pole might be hiding somewhere in the universe. The answer begins simply, but it does not remain small for very long. Still, there is something pleasing about the everyday demonstration. You do not need a particle accelerator to see the basic rule. Break a bar magnet, test the pieces, and each one behaves as a complete magnet. Break those pieces again, and the pattern repeats. The experiment is almost calm in its consistency. Nature does not hesitate or negotiate. North and south return every time. It is as though the magnet carries a blueprint through its entire body, and each fragment remembers enough of that blueprint to rebuild the same basic arrangement. Of course, a magnet does not remember in the conscious sense. It has no opinion about being cut and no desire to preserve tradition. The persistence comes from the physical state of the material. The atoms and electrons remain arranged in ways that produce magnetism. When a new boundary appears, the field associated with that arrangement appears at the boundary as well. The new ends are not replacement parts created after damage. They are simply new places where the existing magnetic order meets the surrounding space. This distinction is important because it changes the question from where are the poles stored to how is the entire magnet organized. Once we ask the second question, the strange behavior begins to make sense. The poles are not objects hidden at the ends, they are features of a pattern. Cutting changes the size of the pattern, but it does not change the kind of pattern it is. A small whirlpool still has circulation. A short piece of a repeating design still contains the design. A smaller magnet still has magnetic order, and therefore still has two poles. There are limits to these comparisons, and we will move carefully when we reach them. Magnetism is not merely a visible arrangement copied at smaller scales. It is rooted in quantum mechanics, and quantum mechanics has a habit of allowing familiar words while quietly changing what they mean. Electrons have magnetic moments. Atoms can carry magnetic moments. Groups of atoms form domains. Domains can shift, rotate, grow, or shrink. Some materials become permanent magnets. Others respond only while an external field is present. Heat can disturb magnetic order. Strong impacts can change it. Tiny particles can behave differently from large pieces. The simple bar magnet is therefore the surface of a much deeper story. For now, we can keep hold of the central clue. The north and south poles of a magnet are not independent pieces waiting to be separated. They are opposite ends of one magnetic arrangement. Slice through the arrangement and you create another arrangement with another pair of ends. The cut does not reveal a hidden border between north material and south material because no such border exists. Instead, the magnet is magnetic throughout, and the ends merely show us how that internal order connects with the space around it. As we settle into that idea, the familiar labels north and south deserve a closer look. They sound like two different kinds of magnetic substance, but they are really names for two sides of a relationship. One points the way a compass tends to turn, the other points the opposite way. Bring matching poles together and the magnets resist. Bring opposite poles together and they pull close, often with enough enthusiasm to pinch a finger and end the scientific mood rather abruptly. To understand why the poles always remain paired, we first need to understand what those labels mean, how the field is arranged around them, and why a magnet can have two distinct ends without being made from two distinct magnetic halves. North and south sound like two separate things. We use the words for opposite directions on a map, opposite ends of the planet, and opposite points on a compass. If someone travels north, they are not also travelling south. If a road leads one way, the other direction lies behind them. So when we hear that a magnet has a north pole at one end and a south pole at the other, it is natural to imagine two distinct magnetic ingredients living in different parts of the object. One end contains northness, the other contains southness, and the middle simply keeps them apart. It is a tidy picture, easy to remember, and almost completely misleading. The poles of a magnet are not separate substances. They are not stored in little compartments at opposite ends. They are not magnetic versions of salt and pepper waiting to be poured into different dishes. North and south are names for the two sides of one continuous magnetic arrangement. You can point to one end and call it north, and you can point to the other and call it south, but neither pole makes sense entirely by itself in an ordinary magnet. Each is defined partly by the existence of the other. You can see this relationship with two bar magnets. Bring the north end of one close to the north end of the other, and you feel resistance. The magnets push apart. Turn one around so that north approaches south, and they pull together. The attraction can be gentle or surprisingly strong, depending on the magnets involved. Small magnets may snap together fast enough to make you wonder why your fingertips agreed to participate in the experiment. The rule is simple. Like poles repel, opposite poles attract. That classroom rule is useful, but it can also encourage the idea that poles are objects sitting on the ends. In reality, the behaviour comes from the field surrounding the magnets. A magnetic field is a condition in the space around a magnetic object. Place another magnet in that region, and it experiences a force. Place a compass there and the compass needle turns. Scatter iron filings nearby, and they arrange themselves into curved patterns. Nothing visible is flowing through the space, yet the influence is present. Physicists use field lines to represent this invisible structure. Around a simple bar magnet, the lines curve outward from the north end, sweep through the surrounding space, and enter the south end. Inside the magnet, the pattern continues back toward the north. The full path is a loop. The lines do not truly begin at north and vanish at south. They continue through the material and return to where they started. It is important to remember that field lines are drawings, not physical strings. There are no invisible threads packed around a magnet like hair around a brush. A field line simply shows the direction a tiny north-seeking test pole would move if such a free test pole could be placed there. Since isolated magnetic poles have not been found in ordinary matter, that test object remains imaginary. Still, the drawing gives us a helpful map. Near the poles, the field lines are usually drawn closer together because the magnetic field is stronger there. This is why iron objects are often pulled most strongly toward the ends of a bar magnet. It also explains why we notice the poles as distinct regions. The field is not absent from the middle, but the external effect is concentrated near the ends where the internal magnetic pattern meets the surrounding space. Suppose you place a sheet of paper over a bar magnet and sprinkle iron filings across it. Each tiny piece of iron becomes temporarily magnetized by the field. The filings turn and line up with one another, forming curved bands between the ends. Tap the paper lightly and the pattern becomes clearer. The result looks as if the magnet has drawn its own invisible influence on the page. The filings do not show a straight stream travelling from one end to the other. They show curves. Near the North Pole, they fan outward. Around the sides, they bend. Near the South Pole, they return inward. The image reveals that magnetism is not simply a force stretched across the length of the bar. It surrounds the entire object. A compass gives another view of the same arrangement. A compass needle is itself a small magnet mounted so that it can turn. When it is placed near a larger magnet, it rotates until it lines up with the local field. Move it to a different position, and it turns again. By carrying the compass slowly around the bar magnet and noting the direction at each point, you could trace the field one small step at a time. The end of the compass needle marked north points roughly along the magnetic field. That naming creates a slightly confusing fact about Earth. The north-seeking end of a compass points toward the geographic north. Since opposite magnetic poles attract, the region near the geographic north behaves physically like a magnetic south pole. In everyday conversation, however, people often call it magnetic north, because it lies in the northern part of the planet. Magnetism has managed to make a compass useful while making its terminology mildly irritating. Earth behaves approximately like a giant magnet, though not a perfectly simple one. Deep within the planet, moving electrically conducting material in the liquid outer core generates a global magnetic field. The exact process is complex, involving heat, rotation, flowing metal, and feedback within the field itself. The result gives Earth a pair of broad magnetic regions and a field stretching far into space. The magnetic poles of Earth do not remain fixed. They wander over time because the motion inside the core changes. They have even reversed many times in the geological past. During a reversal, the global field weakens and reorganizes before the overall direction flips. A compass that pointed toward one geographic region during one era would have pointed the other way during another. This tells us something important. North and south are not permanent materials embedded in specific locations. They describe orientation. Reverse the direction of the magnetic field and the labels exchange places. The end that was north becomes south, and the end that was south becomes north. Nothing needs to be removed from the magnet. The internal magnetic order simply turns around. You can sometimes reverse a magnet by placing it in a sufficiently strong magnetic field pointing the opposite way. The process changes the alignment of regions inside the material. Once enough of the internal structure has flipped, the external poles reverse. The physical bar may look exactly the same. It has not been painted, cut, or rotated. Yet what used to attract one end of a compass now attracts the other. This would make little sense if north and south were two different chemicals stored at opposite ends. It makes much more sense if they are consequences of direction. A magnet has an orientation. One end is defined as north, because of the way the field points outward there. The opposite end is south, because the field points inward there. Reverse the orientation, and the roles switch. A helpful comparison is a flowing loop of water in a closed pipe. At one side of the system, the water moves upward. At another side, it moves downward. Those directions are different, but they belong to the same circulation. You could label one side rising and the other falling, but you would not conclude that the pipe contains rising water as a separate substance from falling water. It contains one continuous movement whose direction differs from place to place. The magnetic field around a bar magnet has this kind of connected structure. Although no ordinary fluid is flowing, the north and south poles are places where the field has opposite orientations relative to the surface. They are not isolated supplies of magnetic force. They are parts of one looping pattern. This connection explains why a bar magnet always has two poles. If the magnetic field loops, then the part emerging from one region must return through another. The outward direction and the inward direction come together. A north pole without a south pole would require the field to begin somewhere without returning, rather like a river pouring forever from a spring with no source and disappearing without reaching anywhere else. Electric fields can behave that way because isolated electric charges exist. An electron produces an electric field associated with its negative charge. A proton produces one associated with positive charge. Field lines can begin on positive charge and end on negative charge. A region can contain extra electric charge of one sign without an equal charge sitting beside it. Magnetism seems to follow a different rule. We can create one end of a magnet, but only by also creating the other. Every magnetic source we observe in ordinary materials behaves as a dipole, meaning it has two poles. Even the magnetic character of an electron acts like a tiny dipole. It has an orientation and produces a field with paired sides. This does not mean the electron contains a miniature north half and south half. An electron is not known to be a little bar with internal ends. Its magnetic property is fundamental. The dipole pattern appears in the field around it. The field has one orientation on one side and the opposite orientation on the other, but the electron itself is treated as a quantum object without the ordinary internal shape we might imagine. When many electrons in a material contribute magnetic effects, their orientations matter. If they point randomly, the different fields mostly cancel. One tiny magnetic contribution points one way, another points differently, and the whole object produces little overall field. This is common. Most objects around you are not permanent magnets, even though they are made of atoms containing electrons. In certain materials, interactions between neighbouring electrons encourage groups to align. When many magnetic contributions point in similar directions, they reinforce one another. A larger magnetic pattern appears. The object develops a clear orientation, and the two ends become recognisable as poles. The poles therefore depend on the internal direction of the magnetic order. Imagine a large group of tiny arrows all pointing toward one end of a bar. At that end, the arrows point toward the surface in one way. At the other end, they point relative to the surface in the opposite way. The external field reflects this arrangement. Now imagine cutting the bar across the middle. The arrows in the left piece still point in the same direction they did before. The arrows in the right piece do as well. Each piece now has a new surface where the cut was made. Because the internal order reaches that surface, the cut reveals a new pole on each fragment. The original north end remains the north end of one piece. Its newly cut end behaves as south. The original south end remains the south end of the other piece. Its newly cut end behaves as north. You began with one pair and ended with two pairs. The poles appear at the new surfaces because the field must still connect with the internal magnetic order. The cut has not separated two stored substances. It has created new boundaries in a material that is magnetic throughout. Each boundary becomes part of the new external field pattern. You can repeat the process. Cut each half again, and 4 smaller magnets appear. Each has north and south. Continue, and the pieces become smaller, but the paired structure remains. Eventually the fragments may become so small that heat and random motion can disturb their magnetic stability. Their magnetization may fluctuate or become difficult to preserve. Even then, the basic magnetic contribution remains dipolar rather than turning into an isolated ordinary pole. There is a small complication when a magnet breaks. The new pieces may not always behave as perfect strong magnets. Cutting, heating, striking, or grinding can disturb the internal alignment. Some regions may rotate. Others may become disordered. The overall magnetism can weaken. A brittle magnet may shatter into pieces whose poles are not neatly positioned at the obvious geometric ends. But none of this produces a lone pole. It simply creates more complicated dipoles. A fragment might have several regions pointing in different directions, making its external field irregular. It may attract strongly in unexpected places, yet when the full magnetic structure is mapped, the field still forms connected loops. This is why the phrase "one pole at each end" is a simplification. It works well for a uniformly magnetized bar, but real magnets can have more complicated pole patterns. A ring magnet may have north on one flat face and south on the other. Some magnets are manufactured with alternating poles around their surfaces. Refrigerator magnets often have narrow bands of north and south, placed close together so they grip a metal surface efficiently while producing less field on the outward side. Run a small compass across a flexible refrigerator magnet, and the needle may flip repeatedly. The magnet does not have only one north edge and one south edge. It contains a sequence of magnetized stripes. Each north region lies beside a south region, and the overall design still respects the paired nature of the field. Engineers use these patterns deliberately. By arranging poles in specific ways, they can shape where the field is strong and where it is weak. Electric motors use carefully positioned north and south regions to create rotation. Loudspeakers use magnetic fields to move a coil and push air. Magnetic locks, sensors, generators, and medical scanners all depend on controlling field direction. The poles are not merely labels added after the device is built. Their arrangement determines how the magnetic forces act. A motor works because magnetic fields push and pull in a sequence. If every surface behaved as the same pole without an opposite partner, the field would not form the controlled loops required for the machine. There is also a practical reason magnets often seem strongest at their poles. Inside a long magnet, much of the field is guided through the material. At the ends, the field emerges into the surrounding air, where it can interact with other objects. The concentration of the field near those surfaces produces strong attraction. Different shapes alter this distribution. Bend a bar magnet into a horseshoe shape, and the north and south poles move close together. The field becomes concentrated in the small gap between them. Place a piece of iron across the gap and the magnet can hold it strongly because the iron provides an easy path for the field. Iron is not simply being grabbed by one pole, it becomes temporarily magnetized. The nearby field encourages magnetic regions inside the iron to align. The side closest to a north pole develops south-like behavior and is attracted. Near a south pole, the iron develops north-like behavior. The interaction involves both sides of the magnetic relationship. This is why either pole of a magnet can attract an ordinary iron nail. The nail does not need to know whether it is meeting north or south. Its internal magnetic structure responds to the approaching field. The end nearest the magnet takes on the opposite orientation, producing attraction. Two permanent magnets behave differently because each already has a strong fixed orientation. Place matching poles together, and their field patterns resist being joined in that arrangement. The magnets experience a force pushing them apart. Place opposite poles together, and their fields connect more smoothly, producing attraction. Saying that like poles repel and opposites attract is therefore a compact description of how the field configurations interact. It is not evidence that poles are little personalities with preferences. The North Pole is not offended by another North Pole. The South Pole is not lonely. The forces come from how the electromagnetic field changes as the magnets move. If you push matching poles together, you do work against the repulsion. Energy is stored in the combined magnetic field. Release the magnets and they move apart, converting that stored energy into motion. If opposite poles are separated, you must also do work. Release them and they snap together. This energy belongs to the field and the arrangement of the magnets. The system has different amounts of stored energy depending on position and orientation. The magnets move toward arrangements with lower energy, much as a ball rolls downhill. A freely suspended bar magnet turns until it aligns with Earth's magnetic field. One end points roughly toward geographic north, which is why it is called the north-seeking pole. The other points south. The magnet does not move that way because the northern direction contains a special attractive substance. It rotates because the external field exerts a turning effect on its dipole orientation. This turning effect is called torque, although we can understand it without calculation. The field pulls and pushes on the two sides of the magnet in a way that twists the bar. When the magnet lines up with the field, the twisting effect becomes smaller. It settles into the preferred direction, unless the table shakes or someone places a large speaker beside it and gives the compass a very confusing afternoon. The fact that a compass rotates rather than simply flying northward is another clue that magnetism comes in pairs. Earth's field acts differently on the two ends of the needle. One end is urged one way, and the other end the opposite way, creating rotation. If the needle carried only a single isolated pole, it would be pushed in one direction without the same paired turning behavior. Physicists remain interested in whether true isolated magnetic poles might exist. Some theories predict magnetic monopoles as fundamental particles. A monopole would change the structure of magnetic fields in a profound way. Field lines could begin or end on it, much as electric field lines begin or end on electric charges. No confirmed fundamental monopole has been detected. This absence is not proof that none exist anywhere. They might be extremely rare, extremely massive, or produced only under conditions found in the very early universe. Sensitive experiments continue to search for signs of them. Even without fundamental monopoles, certain materials can produce collective excitations that behave in monopole-like ways. In those systems, complicated arrangements of many magnetic moments create effective sources and sinks within the material. These are valuable for research, but they are not loose north and south poles cut from an ordinary magnet. For the magnet in your hand, the rule remains firm. North and south come together because they are two sides of one magnetic field pattern. The ends can move, the poles can reverse, the shape can change. the magnet can be divided into smaller pieces, yet the paired structure persists. Once that is understood, cutting the magnet no longer seems like a failed attempt to separate two substances. The cut simply reveals that the magnetic order was present all along, not only at the ends but throughout the material. The poles were visible signs of a deeper arrangement. That deeper arrangement is not perfectly uniform inside every magnet. Real materials are divided into magnetic regions, each containing many atoms whose magnetic effects tend to point together. These regions are called domains. In an unmagnetized piece of iron, the domains may point in different directions and cancel. In a magnet, many domains have been encouraged to line up. The behavior of those hidden regions explains how an ordinary piece of metal becomes magnetic, why striking or heating a magnet can weaken it, and why cutting produces new poles instead of separating the old ones. To move from the visible ends into the interior, we need to shrink our view from the bar in your hand to the crowded atomic landscape inside it, where countless tiny magnetic regions decide whether to cooperate, cancel, or quietly change direction. A solid bar magnet looks like one continuous object. Its surface may be smooth, painted, coated in metal, or hidden inside plastic, but nothing on the outside suggests that its magnetic behavior is divided into smaller regions. Hold it near a paperclip and the clip moves. Bring it near a compass and the needle turns. Place it beside another magnet and the two objects pull together or push apart. The entire magnet seems to act as one organised piece, as though every atom inside has attended the same meeting and agreed on a direction. The reality is more crowded. Inside a magnetic material are tiny regions called magnetic domains. Each domain contains an enormous number of atoms, and within that region, many of their magnetic effects point in roughly the same direction. One domain may point toward one side of the object, another may point upward, a third may point at an awkward angle, apparently refusing to cooperate with anyone nearby. Whether the whole object behaves like a strong magnet depends largely on how these domains are arranged. This is one of the most important steps in understanding why cutting a magnet produces smaller magnets. The magnet is not simply magnetic at its ends, its magnetic organisation extends through its interior. The visible poles are the outward result of what countless microscopic regions are doing inside the material. To picture a domain, imagine a large room filled with tiny compass needles. Every needle in that room points in nearly the same direction. Next door is another room containing another group of needles, but they may point somewhere else. The walls between the rooms mark boundaries where the magnetic direction changes. A piece of iron can contain a great many such rooms, each with its own preferred orientation. Of course, there are no literal rooms inside the metal. Domain boundaries are not empty cracks or physical partitions that could be seen with an ordinary microscope. They are transition regions where the direction of magnetic alignment gradually changes from one orientation to another. The material remains solid and continuous. What changes is the pattern formed by the magnetic behavior of its atoms. In an ordinary piece of unmagnetized iron, the domains often point in many different directions. Each domain may be strongly magnetic by itself, but when all of them are considered together, their effects mostly cancel. One region produces a field one way, another produces a field the opposite way, and many others contribute in between. From outside, the piece of iron may show very little overall magnetism. This can seem surprising. A nail that does not behave like a permanent magnet may still contain many strongly magnetized domains. The magnetism is present locally, but it lacks a shared direction. It is rather like a crowd in a train station where everyone is walking with purpose, but not toward the same platform. There is plenty of movement, yet the crowd as a whole does not travel anywhere. A permanent magnet is different because many of its domains are aligned in a common direction. Some may not be perfectly aligned, and the internal arrangement can be complicated, but enough regions cooperate to produce a strong overall magnetic field. Their individual effects add together instead of cancelling. The process of turning suitable material into a magnet often involves placing it in a strong external magnetic field. That field encourages domains already pointing in a favourable direction to grow. Domains pointing elsewhere may shrink, rotate, or change orientation. As the internal balance shifts, the material develops a stronger net magnetization. The word grow may sound as though a domain is consuming neighbouring atoms, but what changes is the boundary between regions. Suppose two neighbouring domains point in different directions. Under an external field, one orientation may be more favourable. The boundary can move, allowing the favoured domain to occupy more of the material. The atoms do not march across the object. Instead, their magnetic orientation changes as the boundary passes through. This happens in steps rather than as one perfectly smooth motion. The boundaries can become caught on imperfections in the material. Tiny defects, impurities, changes in crystal structure, and internal stresses can hold them in place. A stronger field may be needed to dislodge them. When a boundary finally breaks free, it can move suddenly. Scientists can detect these abrupt changes in magnetization. They are known as Barkhausen jumps, named after the physicist who studied them. If a coil of wire is placed around a piece of magnetic material while the field changes, the movement of domain boundaries can create a series of tiny electrical pulses. Amplify them through a speaker, and the magnetization process produces crackling sounds. The metal does not become magnetic in perfect silence at the microscopic level. Its internal regions adjust through countless small jumps, like a crowd rearranging seats one cluster at a time. The sound is not atoms shouting instructions at one another, although that might make materials science easier to explain. It is the electrical response to sudden changes in the magnetic pattern. Different magnetic materials handle their domains in different ways. In soft magnetic materials, domain walls move relatively easily. The material can become strongly magnetized when an external field is applied, but much of that magnetization disappears when the field is removed. Soft iron is a familiar example. It responds readily to a nearby magnet, but does not always retain a strong permanent field. This makes soft magnetic materials useful in devices where magnetism must be switched on and off. An electromagnet often uses a soft iron core surrounded by a coil of wire. When electric current flows through the coil, it produces a magnetic field that aligns domains in the iron. The core becomes strongly magnetic. When the current stops, the domains become less aligned and much of the field fades. Hard magnetic materials behave differently. Their domain boundaries are more strongly pinned by the internal structure. Once the domains have been aligned, they resist changing direction. This allows the material to remain magnetized after the external field is removed. Permanent magnets are made from materials chosen and processed to preserve this alignment. The word hard here does not simply mean difficult to scratch. It refers to magnetic hardness, the ability to resist being demagnetized. A physically hard material may not be a good permanent magnet, and a useful magnetic material may have other mechanical properties that are less convenient. Some strong magnets are brittle and can crack or shatter if dropped, which is nature's way of reminding us that impressive magnetic strength does not necessarily come with good manners. The crystal structure of the material matters greatly. Atoms in a solid are arranged in repeating patterns, and certain directions within that structure can be magnetically easier than others. These are called preferred directions of magnetization. The magnetic moments of atoms tend to settle along these orientations because doing so requires less energy. Imagine a marble resting in a tray with several grooves. It naturally falls into one of the grooves and resists being pushed out. In a magnetic crystal, the atomic magnetic orientation may prefer certain directions in a similar way. An external field can force it toward another orientation, but when the field is removed, the structure influences where it settles. Manufacturers can use this behavior when creating magnets. Materials may be heated, pressed, cooled, or exposed to fields during production, so that their internal grains and preferred magnetic directions support a strong, stable alignment. The finished magnet may look like a simple block, ring or disc, but its performance depends on careful control of structures far too small to see. Not every magnet contains large domains. Size changes the story. If a piece of magnetic material becomes sufficiently small, it may become energetically unfavourable to divide into several domains. Creating a domain boundary costs energy, and in a very small particle, maintaining multiple regions may require more energy than allowing the entire particle to point in one direction. Such a particle can become a single domain. Its magnetic order behaves more like one unified unit. This does not mean it contains only one atom. A single domain particle may still contain many thousands or millions of atoms. It simply means that the magnetic orientation remains broadly consistent throughout the particle. Single domain particles are important in magnetic recording, medicine, sensors, and nanotechnology. Their behavior can be highly stable under some conditions, but at extremely small sizes, another effect becomes important. Thermal motion can cause their magnetic direction to fluctuate. Heat is constant microscopic agitation. Atoms vibrate, particles move, and ordered structures are continually disturbed. In a tiny magnetic particle, the energy barrier holding its magnetization in one direction may become small enough that thermal motion occasionally flips it. Over time, the particle may no longer maintain a fixed magnetic orientation. This behavior is called superparamagnetism. The particle can respond strongly to an external magnetic field, but without that field, its direction may wander rapidly enough that its average magnetization appears to vanish. The particle is still magnetically active, it simply cannot hold one direction for long. This creates a practical limit for storing information in very small magnetic regions. A digital bit may be represented by magnetization, pointing one way or the opposite way. If the region becomes too small and thermal motion flips it randomly, the stored information becomes unreliable. A computer file could slowly forget itself, which is not a feature most users request. Engineers therefore balance size, stability, and magnetic strength. Smaller regions allow more information to be stored in the same space, but they must remain stable for years. Materials are designed with strong preferred orientations and energy barriers that help preserve the magnetic state. The same competition between order and heat appears in larger magnets. Raise the temperature enough, and the atomic magnetic alignment becomes increasingly disturbed. At a particular temperature known as the Curie temperature, the long-range magnetic order of a ferromagnetic material breaks down. Above this temperature, the material no longer behaves as a ferromagnet. Its atoms still carry magnetic properties, but thermal agitation prevents them from maintaining the organized alignment required for permanent magnetism. Cool the material again, and magnetic order can return, although the domains may settle in different directions. The object may not recover its original strong magnetization unless it is exposed to another field. This is why heating a magnet strongly can weaken or destroy its magnetism. The heat does not melt away a supply of magnetic fluid. It disrupts the alignment of the domains and the atomic magnetic moments within them. Once the coordinated pattern is lost, the external field becomes weaker. Striking or dropping a magnet can also disturb its domain arrangement. Mechanical shock sends vibrations and stress through the material. Domain boundaries may shift, and some regions may turn away from the overall direction. Repeated impacts can reduce the magnet's strength, especially in materials whose magnetic state is not strongly locked in place. There is an old classroom method of magnetizing a steel needle by stroking it repeatedly with a magnet in one direction. Each pass exposes the needle to a magnetic field that encourages some domains to align. Repetition increases the overall order. Stroking back and forth carelessly can reduce the effect because the changing direction encourages different alignments. A similar principle explains why an iron object near a magnet becomes temporarily magnetized. The external field causes favorable domains to grow and others to shrink. The side nearest the magnet develops a pole opposite to the approaching pole, creating attraction. Remove the magnet and the iron may lose most of this induced magnetization. Its domain walls move back toward a less organized arrangement. In steel, which is more magnetically resistant, some alignment can remain. The object may become a weak permanent magnet. This difference between easy movement and strong retention is central to magnetic design. A transformer core should change magnetization repeatedly as electrical current alternates. It needs domain walls that can move with little energy loss. A permanent motor magnet should resist change. It needs domains that remain locked even when exposed to opposing fields. The history of a magnetic material can therefore be recorded in its present state. The field it experienced, the temperature it reached, the stress it endured, and the way it cooled can all influence its domains. Magnetism can act as a kind of memory. Rocks provide a powerful example. When certain volcanic rocks cool from molten material, magnetic minerals inside them can align with Earth's magnetic field. Once the rock solidifies below the relevant temperature, that direction becomes locked in place. The rock preserves a record of the planet's field at the time it formed. By measuring the magnetization of ancient rocks, geologists discovered that Earth's magnetic field has reversed many times. They also found symmetrical magnetic stripes on the ocean floor. As new crust formed at mid-ocean ridges, cooling rock recorded the current field direction. Later reversals produced alternating bands. These magnetic patterns became important evidence for seafloor spreading and plate tectonics. Tiny domains inside minerals helped reveal that continents move and oceans grow. A property that begins with electron behavior inside atoms can preserve the history of the entire planet. Some animals also respond to Earth's magnetic field. Birds, sea turtles, fish, insects, and other creatures appear to use magnetic information for navigation. The exact biological mechanisms vary and remain under investigation. In some cases, tiny magnetic particles may contribute. In others, light-sensitive chemical reactions may respond to magnetic direction. Even here, the usefulness of magnetism depends on organized responses at small scales. A weak planetary field can influence behavior because biological systems have developed sensitive ways of detecting it. The field itself is gentle compared with a strong household magnet, yet across long migrations, a rough magnetic compass can be extremely valuable. Returning to the bar magnet, the domain picture now explains why its poles cannot be assigned to separate halves. Suppose the magnet contains many domains aligned from left to right. At the left end, the internal magnetization meets the outer surface in one orientation. At the right end, it meets the surface in the opposite orientation. Those surfaces behave as the two poles. Cut through the middle and the domains in both pieces remain mostly aligned from left to right. The newly exposed right side of the left fragment becomes one type of pole. The newly exposed left side of the right fragment becomes the opposite type. Each fragment has internal order, and therefore each produces its own complete external field. The strength may change because the cutting process can disturb domains. Heat from a saw, mechanical stress, cracks, and rough edges may cause some regions to reorient. The new pieces may not be as strong or as neatly magnetized as the original. Still, any remaining magnetization takes the form of a dipole pattern. If the original magnet contains a complicated arrangement of domains, the fragments may develop poles in unexpected positions. A piece might attract more strongly along one corner than another. Its magnetic axis may not line up with its physical length. This is not evidence of an isolated pole, it simply reflects an irregular internal pattern. One way to see domains directly is through specialized imaging methods. Scientists can apply fine magnetic particles to a polished surface, use electron microscopes, shine polarized light, or detect tiny forces with scanning instruments. The resulting images reveal branching patterns, stripes, patches, and curling arrangements. These patterns can be remarkably complex. domains form shapes that reduce the total energy of the magnetic system. A material may divide into regions so that less magnetic field extends into the surrounding space. Near the surface, the magnetization may curl or form smaller closure domains that help the field loop back through the material. This means a magnet's internal arrangement is not always a simple collection of straight regions, all pointing from one end to the other. The domains compromise between several competing influences. Neighbouring magnetic moments prefer alignment. Crystal structure favours particular directions. Domain walls cost energy. External fields push the pattern one way. The shape of the object affects how the field closes around it. The final structure is the arrangement that balances these demands. It may be orderly without being simple. A rectangular magnet, a thin film, a wire, and a small sphere can develop different domain patterns even when made from the same material. Shape matters because the magnetic field extends beyond the object. A long, thin bar naturally supports magnetization along its length more easily than across its width. A thin, flat film may prefer directions within its surface. A tiny ring can support magnetization curling around the ring, producing little external field. Engineers exploit these effects. By controlling shape at microscopic scales, they can create magnetic sensors, memory elements, and devices whose domains switch in predictable ways. Modern technology often depends not merely on whether a material is magnetic, but on how its internal regions move under carefully applied fields and currents. A loudspeaker relies on a permanent magnet producing a stable field. An electric current passes through a coil in that field, creating motion that pushes the speaker cone. A hard drive stores data in microscopic magnetic regions. A motor arranges magnets so fields produce continuous rotation. Medical imaging systems use powerful electromagnets whose behavior depends on materials designed to carry and control magnetic fields. In every case, the visible machine rests on organization below the surface. The magnet is not an indivisible block of force. It is a coordinated structure made from atoms, electrons, crystal grains, domains, and boundaries. Yet the domain picture is still not the deepest level. It tells us how many atomic magnetic effects become organized across a material, but it does not tell us where each atomic effect comes from. Why does an atom behave magnetically at all? Why do electrons produce magnetic moments? Why do neighbouring atoms sometimes prefer to align while others cancel one another? To answer those questions, the comfortable picture of tiny compass needles must be handled carefully. The atoms inside a domain are not filled with little mechanical magnets. Their magnetic behaviour comes from electrons, from their motion around atomic nuclei, from a quantum property called spin, and from rules that have no perfect counterpart in ordinary everyday objects. The word spin sounds reassuringly familiar. It suggests a ball turning around an axis, a wheel rotating, or a planet completing another day. But an electron does not spin in that ordinary sense. The name survived because some of its effects resemble those of a rotating charged object. Yet the quantum reality is stranger. It gives each electron a built-in magnetic character, without requiring the electron to be a tiny sphere physically whirling through space. Domains explain how magnetism becomes large enough to hold a note on a refrigerator. Electrons explain why there is anything magnetic to organize in the first place. Once the view moves below the domain boundary and into the atom, the solid magnet begins to look less like a collection of tiny bars and more like a quantum system in which invisible properties cooperate across vast numbers of particles. To understand where magnetism really begins, we have to leave the visible magnet behind and move into the atom. This is where familiar pictures become less reliable. A bar magnet can be held, turned, dropped, and occasionally stuck to something it was never meant to touch. An electron cannot be treated in quite the same way. It is not a tiny metal ball moving through the atom like a planet around the sun. It does not have a little painted north end and south end. Yet the magnetic behaviour of ordinary matter begins with electrons, and much of it comes from a quantum property called spin. The word spin is one of those scientific names that is useful and troublesome at the same time. It sounds as though an electron is literally rotating around an internal axis, like a football, a wheel, or a person in an office chair who has briefly forgotten why they sat down. Early physicists used the word because some of the electron's behaviour resembled the magnetism that might be produced by a spinning electric charge. But the comparison cannot be taken literally. As far as experiments can tell, an electron behaves as a point-like particle. It does not have a measurable solid surface that could rotate in the ordinary mechanical sense. If an electron were a tiny charged sphere spinning fast enough to produce its observed magnetic effect, parts of its surface would have to move faster than light. That would conflict with relativity and leave the model in immediate difficulty. The electron is therefore not a miniature spinning ball. Spin is an intrinsic property. It belongs to the electron in the same fundamental way that electric charge and mass belong to it. This can feel unsatisfying at first. We're used to explaining properties by imagining smaller moving parts. A clock ticks because gears turn. A fan moves air because blades rotate. A bicycle rolls because wheels spin. But when physics reaches truly fundamental particles, there may be no smaller mechanism underneath the property. The electron has spin because that is part of what an electron is. Spin gives the electron an orientation in a quantum sense. When scientists measure that orientation along a chosen direction, they find only two possible outcomes. The electron behaves as though its spin points one way or the opposite way. These are often described as spin up and spin down, although the labels depend on the direction chosen for the measurement. The electron does not necessarily possess a tiny arrow that was quietly pointing somewhere before anyone looked. Quantum measurements are subtler than that. The state of the electron can contain a mixture of possibilities relative to a particular direction. When measured, one of the allowed outcomes appears. The details belong to quantum mechanics, where objects are described not by perfectly definite hidden positions and rotations, but by states that determine the probabilities of the different results. For magnetism, the important point is that spin gives the electron a magnetic moment. A magnetic moment tells us how strongly something responds to a magnetic field, and how it tends to orient within that field. It is the property that makes an electron behave somewhat like a tiny magnetic dipole. Place an electron in a magnetic field and its magnetic moment interacts with that field. The electron may favour one orientation over another. In atoms, these magnetic effects influence energy levels, chemical behaviour, and the way neighbouring atoms interact. When enough electrons contribute in an organised way, their tiny magnetic moments can build the field of a permanent magnet. Spin is not the only source of atomic magnetism. Electrons also occupy regions around the atomic nucleus called orbitals. The word orbital is chosen carefully. It does not mean that an electron follows a neat circular path around the nucleus like a moon around a planet. An orbital is a quantum state describing where the electron is likely to be found and how its wave-like behaviour is arranged. Some orbitals carry angular momentum, another quantum property connected with rotational behaviour. Because the electron is electrically charged, this orbital motion contributes a magnetic moment. An atom's magnetism can therefore arise from both the intrinsic spin of its electrons and their orbital angular momentum. In some atoms, the orbital contribution is partly suppressed by the surrounding crystal. The electric fields produced by neighbouring atoms can lock the electron clouds into particular shapes and reduce their ability to contribute freely to magnetism. In other materials, orbital effects remain important and help produce strong magnetic behaviour. A single atom may contain many electrons. If every electron simply added its magnetic moment to the total, nearly all matter would be strongly magnetic. That does not happen because electrons often arrange themselves in pairs. One electron in a pair has one spin orientation, and the other has the opposite orientation. Their magnetic moments largely cancel. Two electrons can share the same orbital only if their spins are opposite. This is a consequence of the Pauli exclusion principle. one of the central rules governing matter. The Pauli exclusion principle says that no two identical electrons in an atom can occupy exactly the same quantum state. Electrons must differ in some part of their description. If two occupy the same orbital, their spin orientations must be opposite. This rule is responsible for far more than magnetism. It helps create the layered structure of atoms, shapes the periodic table, and prevents ordinary matter from collapsing into an undifferentiated pile of particles. It gives chemistry much of its organization and allows tables, walls, planets, and people to occupy space with a reassuring amount of firmness. For magnetism, the rule means that many electrons cancel in pairs. An atom with all of its relevant electrons paired may have little or no permanent magnetic moment. An atom with unpaired electrons can behave differently. Those unpaired electrons contribute magnetic moments that do not have partners pointing the opposite way. Iron, cobalt, and nickel contain electron arrangements that leave important electrons unpaired. This makes their atoms capable of contributing to strong magnetism. But unpaired electrons alone are not enough to produce a permanent magnet. Many materials contain atoms with magnetic moments and still do not remain strongly magnetized. The moments must communicate with one another. They must develop some shared order. The reason this can happen involves one of the strangest effects in quantum mechanics, known as the exchange interaction. The exchange interaction is not an ordinary force like two magnets pushing or pulling across a table. It arises from the quantum nature of identical particles and from the Pauli exclusion principle. Electrons are indistinguishable. There is no physical label attached to one saying electron number 1 and another saying electron number 2. When their quantum states overlap, the combined state must obey strict symmetry rules. These rules affect the energy of different spin arrangements. In some materials, neighbouring electron spins can lower the total energy by aligning in the same direction. If many neighbouring atoms favour that arrangement, large regions of common alignment appear. Those regions become magnetic domains. This is a deeper explanation of the tiny regions we met earlier. The atoms inside a domain do not align because each one notices the North Pole at the far end of the bar and decides to be helpful. They align because quantum interactions between neighbouring electrons make certain collective arrangements energetically favourable. The exchange interaction can be extremely strong compared with the ordinary magnetic force between two electron moments. That is important because the direct magnetic attraction between neighbouring atomic dipoles would usually be too weak to maintain strong order at everyday temperatures. The quantum exchange effect provides the stronger connection. This gives ferromagnetic materials their unusual behaviour. In a ferromagnet, many atomic magnetic moments tend to align in the same direction. Iron is the best known example. Though not every piece of iron is a permanent magnet. The alignment may occur inside individual domains, while different domains point in different directions. Apply an external field, and the domains favourably aligned with it can grow. The atomic moments themselves may also rotate. Once enough of the internal structure points in a shared direction, the material develops a strong overall field. Remove the external field, and the result depends on the material. In soft iron, many domains return toward a less organised arrangement. In a hard magnetic material, crystal structure and internal defects help preserve the alignment. The magnet remains magnetised. The alignment is not absolutely rigid. Temperature constantly disturbs it. Atoms vibrate, electron states fluctuate, and the magnetic moments are jostled by thermal energy. At low enough temperatures, the exchange interaction maintains order. As the material becomes hotter, disorder grows. Above the Curie temperature, the long-range ferromagnetic alignment disappears. The material enters a different magnetic state. Individual atomic moments may remain, but they no longer maintain the shared direction needed for a permanent magnet. The balance resembles a crowded room where everyone has been instructed to face the same way while the floor begins shaking more and more strongly. At first, the group holds its formation. As the shaking increases, some turn aside. Eventually, the orderly arrangement breaks down entirely, and everyone returns to making independent decisions. Not all magnetic materials favour parallel alignment. In some, neighbouring moments prefer to point in opposite directions. This creates antiferromagnetism. One atomic moment points one way, the next points the other, and their effects can cancel almost completely. Antiferromagnetic materials may produce little external field, yet they possess highly ordered internal magnetism. They are not magnetically disorganized. Their order is simply balanced. Another arrangement is called ferrimagnetism. Here, different groups of magnetic moments point in opposite directions, but the groups are unequal. One contribution is stronger than the other, so some magnetism remains. Many ceramic magnets, including materials known as ferrets, work this way. These different states show that magnetism is not merely a question of whether electrons possess spin. Nearly all electrons do. What matters is how the spins and orbital effects combine across the material. They may cancel within atoms, cancel between atoms, reinforce one another, or form complicated patterns. There are also materials called paramagnets. Their atoms or molecules contain magnetic moments that respond to an external field. In the presence of that field, the moments tend to align slightly, producing a weak attraction. Remove the field and thermal motion randomizes them again. Aluminium and oxygen provide examples of paramagnetic behavior. The effect is usually much weaker than the attraction seen in iron. A household magnet will not lift an aluminium spoon from the table, which is probably fortunate for anyone trying to eat soup near a loudspeaker. Diamagnetism is different again. When an external magnetic field is applied, the electron motion in a material adjusts in a way that produces a small opposing field. This causes a weak repulsion. All materials have some diamagnetic response, but it is usually hidden when stronger magnetic effects are present. Certain substances, including bismuth and graphite, show diamagnetism strongly enough to demonstrate visibly. With sufficiently powerful magnets, small pieces can be made to levitate. Living tissue is also weakly diamagnetic because it contains large amounts of water. In extremely strong magnetic fields, even small animals have been levitated in laboratory demonstrations. The animals were not becoming permanent magnets. Their materials were responding weakly against the applied field. Superconductors display an especially dramatic magnetic response. Below a critical temperature, some materials conduct electric current without ordinary resistance and expel magnetic fields from much of their interior. A magnet placed above a superconductor can levitate in a stable way. This behavior belongs to the quantum physics of large groups of electrons acting collectively. It reminds us that magnetic effects can emerge not only from isolated atomic moments, but also from organized currents and shared quantum states across a material. Electric current itself creates magnetism. Pass current through a wire and a magnetic field forms around it. Wind the wire into a coil and the fields from each turn reinforce one another. Add an iron core, and the field can become much stronger as domains in the iron align. This connection between electricity and magnetism is not an accidental resemblance. They are two parts of one electromagnetic phenomenon. An electric charge produces an electric field. A moving electric charge contributes to a magnetic field. A change in magnetic field can push electric charges and create current. From one perspective, magnetism can even be understood as a relativistic aspect of electricity. Observers moving differently can disagree about the balance of electric charges and currents in a system. What appears partly as an electric force from one frame of motion may include a magnetic force from another. This does not make spin-based magnetism simple, because electron spin is an intrinsic quantum property rather than a classical current loop. Yet the broader lesson remains. Magnetism is deeply connected to charge, motion, quantum mechanics, and relativity. The tiny magnetic moment of an electron does not sit motionless like a compass needle fixed inside the particle. In a magnetic field, its orientation can undergo a motion called precession. Instead of pointing directly and remaining still, the magnetic moment can rotate around the field direction, somewhat like the axis of a spinning top circling as gravity pulls on it. Once again, the analogy must be handled carefully because electron spin is not literal mechanical spinning. Still, precession has measurable consequences. It plays an important role in magnetic resonance. Medical scanners use this principle in magnetic resonance imaging. Strong fields influence the magnetic moments of atomic nuclei, especially the nuclei of hydrogen atoms in water. Radio waves disturb their alignment, and as the nuclei return toward equilibrium, they produce signals. Computers use those signals to construct detailed images of tissue. The magnetic behavior used in such scanners is mainly associated with atomic nuclei rather than electron spins, but the underlying idea is related. Quantum particles carry magnetic moments. External fields influence their energy and orientation. Carefully measured responses reveal information about the surrounding material. Electron spin is also central to newer technologies known collectively as spintronics. Traditional electronics mainly uses electric charge to carry and process information. Spintronics also uses the spin orientation of electrons. Devices that detect changes in spin-dependent electrical resistance have made it possible to read magnetic data with great sensitivity. This contributed to major increases in the storage capacity of hard drives. Researchers continue exploring spin-based memory, sensors, and computing systems that may use less energy or preserve information without continuous power. The ordinary bar magnet therefore sits at the end of a long chain of organization. At the smallest level are electrons with charge, spin, and orbital quantum states. Within atoms, their contributions combine or cancel. Between atoms, exchange interactions favor particular arrangements. Across a crystal, magnetic order forms domains. Across the whole object, enough domains align to create a visible north pole and south pole. Every stage matters. Remove unpaired electrons and the atomic magnetic moments may vanish. Change the exchange interaction, and the material may prefer opposite alignment. Heat the solid enough and the order collapses. Break the object and the domain arrangement may shift. Shape the material differently and the external field changes. This also explains why not every piece of metal becomes a permanent magnet. The presence of electrons is universal, but the required arrangement is not. Copper contains electrons and conducts electricity very well, yet it does not form a strong permanent magnet under ordinary conditions. Its electron structure does not support the same stable ferromagnetic ordering found in iron. Even iron does not automatically behave as a bar magnet. A random collection of domains can cancel externally. To create a strong permanent magnet, the internal order must be established and retained. When a magnet is cut, the electron spins and atomic moments inside the pieces do not suddenly divide into north particles and south particles. They remain organized within the new fragments. The exchange interactions continue. The domains continue. The internal magnetization meets the newly exposed surfaces and new poles appear. The reason you cannot isolate a pole by cutting is therefore rooted far below the visible ends. Each electron contributes a dipole-like magnetic moment. Each aligned region contains paired magnetic behavior throughout its structure. The magnet does not contain a row of north objects gathered on one side and south objects gathered on the other. A useful picture is a chain of compass needles placed end to end. Every needle has both poles. In the middle of the chain, the north end of one lies beside the south end of the next, so their external effects partly cancel. At the two outer ends, one pole remains exposed on each side. The whole chain behaves like one larger magnet. Cut the chain, and the two new exposed ends become a new pair of poles. No individual needle has been split. You have simply created two shorter chains. The real material is not literally made from compass needles, but electron magnetic moments and aligned atomic regions produce a related result. Opposite contributions inside the material connect and partly cancel, while the surfaces reveal the overall orientation. A cut creates new surfaces, and therefore a new pair of visible poles. The fact that electron magnetism is dipolar is central. Its field has paired orientation. The ordinary sources of magnetic fields do not behave like isolated north charges or isolated south charges. They behave like loops and dipoles. This does not fully explain why nature apparently allows isolated electric charge while hiding or forbidding isolated magnetic charge. That question remains open. The known particles of the Standard Model include electrically charged particles, but no confirmed magnetic monopole. Some theories suggest that monopoles should exist at very high energies. Others show that introducing even one magnetic monopole could help explain why electric charge appears in exact units. The search continues because finding one would transform physics, yet the magnet on a table does not need a fundamental monopole to work. Its field comes from electric charges, quantum spin, orbital behavior, and collective alignment. Everything needed for ordinary magnetism is already present in the electrons and atoms of the material. The hidden source of the magnet's strength is therefore not a mysterious substance flowing from one pole to the other. It is organized quantum behavior. Billions upon billions of electrons contribute moments that align through interactions built into the rules of matter. Their individual effects are tiny. No one electron could hold a photograph on a refrigerator. Together, arranged across countless atoms and domains, they produce a force strong enough to lift metal, turn motors, store information, and guide compass needles. That collective power is one of the recurring themes of physics. A single water molecule is not a wave, but many molecules can form one. One air molecule does not create a note, but a coordinated vibration becomes sound. A single electron moment is microscopic, but a vast organized population becomes a magnet. Once that population is aligned, cutting the solid does not erase the organization. It divides the population into smaller groups, and each group carries the same basic magnetic structure. The two new pieces may differ in strength or internal complexity, but neither becomes a single isolated pole. The next step is to look directly at that cut. We can imagine marking the original north and south ends, breaking the magnet at the center, and following how the magnetic field rearranges around the fragments. Nothing travels from one end to rescue the other. No hidden reserve of polarity is released. The new poles arise immediately from the same internal order that was already present before the break. Take a bar magnet and place it on a table. Mark one end as north and the other as south. The arrangement looks clear enough. One pole belongs to one side, the opposite pole belongs to the other, and the material between them seems to serve as a bridge. From that simple picture, the result of cutting appears obvious. Slice through the middle and the north end should remain on one piece, while the south end remains on the other. The two poles should finally be separated, each sitting alone on its own fragment. That is not what happens. After the magnet is divided, the piece that kept the original north end develops a south pole at its newly cut surface. The piece that kept the original south end develops a north pole at its new surface. Instead of producing two isolated poles, the cut produces two smaller magnets. Each fragment has a complete north and south pair. Cut those fragments again and the same thing happens. 4 magnets appear. Divide them further and you obtain more magnets, each carrying both poles. The pieces become shorter, weaker, less tidy, and increasingly difficult to handle, but the magnetic pairing remains. This is often presented as though the magnet performs some kind of emergency repair. The blade passes through, the poles notice that they have been separated, and new poles rush into position to restore balance. It is an entertaining picture, but no magnetic repair team is involved. Nothing travels from the original ends toward the cut in order to replace what was lost. The new poles appear because the magnetic order already existed throughout the material before the cut was made. The original poles were simply the places where that internal order met the outer surface. When a new surface is created, the same internal order meets the outside world at a new location. That location behaves as a pole. Imagine a long row of arrows, all pointing from left to right. At the far left, you see the rear ends of the arrows. At the far right, you see their points. Cut the row in the middle and you create 2 shorter rows. Each still has rear ends on one side and points on the other. The cut has not created new arrows, it has exposed parts of the pattern that were previously hidden inside the longer row. Inside a real magnet, the situation is far more complicated than a neat row of arrows, but the basic lesson holds. Magnetic order runs through the material. The poles are consequences of that order at the boundaries. Before cutting, the magnet has two outer ends. At one end, the internal magnetization reaches the surface in one direction. At the opposite end, it reaches the surface in the reverse direction. Those two surfaces produce the familiar north and south behavior. The center of the magnet is not magnetically empty. It may seem less active because an iron object is often pulled most strongly toward the ends, but the atomic magnetic moments and domains in the middle are still part of the organized structure. Their effects connect through the material and contribute to the overall magnetic field. When the blade passes through the center, it does not encounter a neutral zone separating north material from south material. It passes through magnetized matter. The atoms on one side of the cut remain part of one fragment. The atoms on the other side remain part of the second. Their magnetic moments do not suddenly lose their direction, simply because the solid has been separated. Each fragment now has two outer boundaries. One is an original end of the magnet. The other is the newly cut face. Since the internal magnetization reaches both boundaries, each fragment produces a complete external magnetic field. The field around the original magnet changes shape after the cut. Before division, it formed a broad looping pattern around one long object. After division, the field reorganizes around two smaller objects. Each new magnet has lines curving through the surrounding space from its north side toward its south side, while the full pattern continues through the material. On ordinary human timescales, this rearrangement appears immediate. The moment the pieces are separated, they already behave like magnets. There is no pause during which one fragment acts as pure north and the other as pure south. The field responds as the physical arrangement changes. Strictly speaking, changes in electromagnetic fields do not travel infinitely fast. Information about a change propagates at the speed of light. Across the tiny distances of a handheld magnet, however, that travel time is so short that no ordinary experiment could notice it. To your eyes and fingers, the new field is simply there. The two cut faces often behave as opposite poles. If the original magnet was aligned from left to right, the right face of the left fragment may act as south, while the left face of the right fragment acts as north. Bring those fresh faces near one another and they attract, which is exactly what we should expect because they were once neighbouring parts of the same continuous magnetic structure. If you return the pieces to their original positions, the field can resemble the field of the uncut magnet, especially if the gap is very small. The two internal facing poles are close together, and much of their field connects directly across the gap. From farther away, the pair may behave almost like one longer magnet. Move the fragments apart and each field becomes more distinct. A compass brought near one piece will trace a complete magnetic pattern around it. The same is true of the other. The original magnet has not donated half a field to each fragment. It has become two systems, and each system possesses its own dipole field. The strength of the fragments depends on how the magnet was cut, what material it was made from, and how much internal damage occurred. A perfectly clean division in an idealized magnet would leave each piece with much of the original magnetic alignment. Real cutting is rarely so polite. Many permanent magnets are hard but brittle. Ceramic magnets can crack or crumble. Powerful rare earth magnets may chip or shatter. Trying to saw one can create dust, heat, and sharp fragments. Large neodymium magnets can also snap together with enough force to injure fingers, so cutting them is not a sensible kitchen table experiment. Mechanical stress affects domains. As the material bends, cracks, or vibrates, some domain walls may move. Magnetic moments that were aligned may rotate into slightly different directions. The fragments can therefore become weaker than a simple theoretical picture predicts. Heat creates another problem. Sawing or grinding produces friction, and friction raises temperature. If the magnet becomes warm enough, thermal motion disturbs its internal magnetic order. It does not need to reach the Curie temperature to suffer some loss. Many permanent magnets begin weakening well below the temperature at which ferromagnetism disappears completely. The newly cut pieces may therefore have less magnetization than the original. This weakening sometimes leads people to think that part of the magnetism escaped during cutting. Magnetism is not a liquid leaking from the broken surface. The loss occurs because the internal alignment has been disturbed. Shape also matters. A long bar magnet supports a different external field from a short wide block. When the bar is cut across its length, each fragment becomes less elongated. The relationship between its dimensions changes, and that affects how easily the internal magnetization remains aligned. Magnetic materials are influenced by what is called a demagnetizing field. This is an internal effect created partly by the magnet's own shape and surface poles. Certain shapes support magnetization in one direction more easily than others. A long thin bar generally favours magnetization along its length. A short thick piece may experience stronger internal opposition to that same arrangement. After cutting, the new surfaces create additional pole regions. These regions contribute to an internal field that may encourage some domains to turn, split, or form closure patterns. The magnetic state can adjust to reduce the total energy. This adjustment does not remove the paired poles. It can make them less simple. Instead of one clean north face and one clean south face, a fragment may develop smaller regions with different orientations. Some of its magnetic field may close within or near the material, rather than extending far into the surrounding space. A small fragment can therefore have an irregular field. One corner may attract more strongly than another. The apparent pole may not sit exactly at the centre of a face. A compass moved around the piece may turn in ways that do not match the neat diagram from a textbook. None of this produces an isolated pole. It only shows that a real magnet is a complicated collection of domains, rather than a perfectly uniform block. The direction of the cut makes a difference as well. Suppose a long bar magnet is magnetized from one end to the other. Cutting it across the middle produces two shorter magnets, aligned in the same direction as the original. Each gains a new pole at the cut. Now imagine slicing the bar lengthwise, creating two thinner bars running parallel to the original magnetization. In that case, each long piece can still retain the original north and south ends. The new cut surfaces along the sides are not necessarily strong poles because the internal magnetization runs mostly parallel to them. Both pieces still behave as complete magnets. Their field strengths and domain patterns may differ, but neither becomes a north-only or south-only object. If the magnet is cut at an angle, the new surface interacts with the internal magnetization in a more complicated way. Different portions of the face may contribute differently to the external field. The poles may appear spread across the surface rather than concentrated neatly at one point. This reminds us that a magnetic pole is not usually a tiny spot. It is a region where the field enters or leaves the surface in a particular way. In a uniformly magnetized bar, the pole appears concentrated near an end face. In an irregular fragment, the pole distribution can be uneven. The word pole is useful because it describes how the magnet interacts with other fields, but it can tempt us to imagine a separate object. There is no small bead of North Pole material buried at the end. The pole is a feature of the field and the magnetization pattern. Iron filings can make the change visible. Place the original magnet beneath a sheet of paper and sprinkle filings above it. The filings arrange themselves into curved patterns connecting the two ends. Remove the magnet, cut it, and place the fragments far apart beneath the paper. Around each piece, a separate curved pattern appears. The filings reveal a north and south arrangement for both fragments. Place the cut faces close together, and the patterns join strongly across the gap. Move the fragments farther apart and the loops spread through the surrounding space. The field has adjusted to the new geometry. A compass offers a slower but clearer map. Move it around the first piece and observe how the needle turns. It traces a loop around that fragment. Repeat the process around the second piece, and another loop appears. No point around either fragment behaves as though the field simply bursts outward forever without returning. The field remains continuous. That continuity is one reason cutting cannot isolate a pole. Electric charge gives us a useful contrast. A positively charged object and a negatively charged object can be separated. One can be carried to one side of a room and the other to the opposite side. Their electric fields extend outward according to the charge present. Magnetic poles in ordinary matter do not behave as independent charges. The sources of the magnetic field are dipoles, currents, electron spins, orbital motion, and organized atomic moments. These produce looping field patterns. Cutting a wire carrying electric current also does not give one half of its magnetic field to each piece. If the current stops, the field associated with that current changes. If separate currents are established in the new pieces, each creates its own field. The magnetic behavior depends on the complete physical arrangement, not on pieces of field being stored like portions of rope. A permanent magnet is different from a powered wire because its internal electron organization maintains the field without an external current supply. Still, the field belongs to the whole state of the material. Change the shape, and the field changes with it. Energy is involved in this rearrangement. Cutting the magnet requires mechanical work. Chemical bonds and crystal structures must be broken to create new surfaces. The magnetic configuration also acquires new energy, because new pole regions and fields appear. The new fragments may settle into slightly different domain arrangements that lower their total energy. Some magnetic energy can become heat, vibration, or sound during the break. Anyone who has heard a brittle magnet snap has witnessed a small and rather abrupt redistribution of energy. If the pieces are allowed to move freely after being cut, their fresh opposite poles may attract. They can turn and snap back together. This does not mean the magnet is trying to heal. The magnetic force simply pulls the system toward a lower energy arrangement. Put the fragments together exactly as they were, and many of the new internal facing pole effects cancel across the narrow gap. The external field again resembles that of one longer magnet. Pull them apart and you must do work against the attraction. Turn one fragment around before bringing the cut faces together and the result changes. Matching poles may now face one another, producing repulsion. The pieces resist being joined in that orientation because the combined field carries more energy. The magnet can therefore remember direction even after its physical continuity has been lost. The fragments preserve much of the original internal alignment, allowing us to identify which surfaces once faced each other. Some magnets are manufactured from many small magnetic grains bound together. In a bonded magnet, magnetic powder is mixed with a polymer and shaped into a useful form. Cutting such a magnet separates groups of already magnetized grains. Each piece still contains grains whose magnetic moments contribute to a complete field. The new fragment may be weaker because of its size, grain arrangement, and disturbed boundaries, but it remains dipolar. Other magnets are sintered, meaning magnetic powder is compressed and heated so particles bond into a solid. Their internal grains may have preferred orientations established during manufacturing. Cutting across them can expose surfaces that chip easily and can disturb coatings used to protect the material from corrosion. The practical result remains the same. The internal order survives within each fragment enough to create both poles. At sufficiently small scales, the idea of physically cutting becomes less straightforward. You cannot continue using a blade until only one electron remains on each side. Materials eventually become collections of tiny grains, clusters, atoms, and particles. Their magnetic behavior changes as size decreases. A small magnetic particle may contain only one domain. Its entire magnetization points broadly in one direction. Yet it still behaves as a dipole, with a north-like side and a south-like side in its field. Make the particle even smaller, and thermal agitation may cause its magnetization to flip. Over time, the average field may appear to vanish. The particle has not become a monopole. It has become unable to hold a stable dipole orientation. At the atomic level, electrons and nuclei carry magnetic moments. These moments are also dipolar. They cannot be sliced with a saw into separate north and south halves. They are quantum properties of the particles. This is where the everyday cutting experiment connects with fundamental physics. Every time a magnet breaks and produces two complete magnets, it reflects the nature of the known microscopic sources of magnetism. Those sources do not consist of independent north and south charges. They produce paired, looping fields. A true magnetic monopole would behave differently. If such an object existed and could somehow be trapped inside a material, cutting might in principle separate magnetic charge in a way ordinary magnets cannot. One fragment could contain a net north magnetic charge, and another a net south magnetic charge. No confirmed fundamental monopole has been found. Every ordinary magnet examined so far follows the paired rule. Break it, grind it, melt it, or reduce it to tiny magnetic particles, and the magnetism comes from dipoles and currents. Melting a magnet deserves a moment of attention because it differs from cutting. If a ferromagnetic solid is heated enough to melt, it usually passes above its Curie temperature along the way. The organized magnetic domains disappear. The liquid may still respond weakly to magnetic fields, but it no longer behaves like the original permanent magnet. Cool the material again, and ferromagnetic order may return below the relevant temperature. The new solid can form domains pointing in many directions. Unless it is magnetized during or after cooling, it may not regain the original strong external field. The north and south poles have not been separated by melting. The organized state that produced them has been destroyed and later replaced by a new arrangement. Breaking at room temperature is gentler in comparison. Much of the magnetic order remains. The fragments inherit the direction of the original magnetization, which is why their poles appear in predictable locations. The phrase inherit is only a convenient description. No information is copied from a parent magnet to its offspring. The pieces simply retain the local state they already had before separation. The atoms near the left end were aligned a certain way before the cut and remain broadly aligned that way afterward. The atoms near the right end do the same. The middle already carried the same organized direction, so when it becomes exposed, its pole behavior becomes visible. This is the central event during the cut. A hidden interior becomes an exterior. What was once surrounded by more magnetized material now touches air, paper, iron filings, compass needles, and the rest of the world. The magnetic field must connect through that new boundary, and the boundary acts as a new pole region. Nothing fundamental has been created at the cut beyond new surfaces and a new field arrangement. There are no new electrons added, no new kind of magnetic particle appears. The same material with the same underlying quantum properties has simply been divided into smaller systems. That is why the answer feels surprising only when the poles are imagined as separate contents. Once they are understood as the ends of an organized dipole pattern, the result becomes almost unavoidable. Divided dipole made from smaller dipoles and each fragment remains dipolar. The next puzzle lies in that word unavoidable. It is one thing to observe that every fragment gains a new pair of poles. It is another to understand why the field must take that form and why nature does not allow one fragment to keep an unmatched magnetic end. To see that more clearly, we need to follow the field through the material and around the surrounding space, watching how every apparent beginning is connected to a return path, and how each new boundary turns one magnetic pattern into another complete pair. Once a magnet has been cut, the most tempting description is that each fragment grows a new pole. The word grows makes the process sound almost biological, as though the pieces notice something missing and begin producing replacements. But the new poles do not develop slowly, and the fragments do not rebuild anything. The poles appear because the cut changes where the existing magnetic order meets the outside world. Before the cut, the internal magnetization runs through one continuous object. At the original ends, that organised direction reaches the surface and produces the familiar north and south behaviour. In the middle, the same magnetic order is present, but it is surrounded by more magnetised material. There is no exposed boundary there, so it does not behave like the outer end of the bar. When a blade or fracture opens the middle, the internal arrangement is suddenly exposed. What used to be buried inside the magnet becomes a surface. On one fragment, the magnetic orientation reaches that new surface in one direction. On the other fragment, it reaches the new surface in the opposite direction. Those two fresh surfaces behave as opposite poles. This is why the new poles always arrive as a pair. The cut creates two surfaces facing one another. The internal magnetic order on one side points toward one of them in a way that produces north-like behaviour. On the other side, the same original order produces south-like behaviour. One cut gives two boundaries, and the two boundaries reveal the two sides of the same magnetic pattern. Imagine a long loaf containing arrows made from different coloured layers. Every arrow points from one end of the loaf toward the other. From the outside, only the first tails and the final arrowheads are visible. Slice the loaf through the middle, and the new faces reveal another set of tails and arrowheads. You have not manufactured new arrows. You have simply exposed parts of the repeating structure that were hidden inside. A magnet is not made from painted arrows, but its internal magnetic moments have an orientation. The analogy helps because it shifts our attention away from the idea that poles are objects stored at the ends. The ends are important only because they are boundaries. When the number of boundaries increases, the number of places where pole behaviour appears also increases. The field surrounding the fragments must adjust to those new boundaries. Before the cut, the magnet produces one broad field extending through and around the whole object. After the cut, each fragment produces a smaller field of its own. The two field patterns may interact strongly if the pieces remain close together, but each one forms a complete magnetic system. If the freshly cut faces remain almost touching, the field between them is concentrated in the narrow gap. Since the faces are opposite poles, much of the field passes directly from one to the other. From a distance, the two fragments can still resemble one long magnet, because their combined field does not change very much. Pull them apart and the field stretches and reorganises. Each fragment now has more space around it, and its field curves through that space before returning to the opposite end. The original magnet has become two independent dipoles. A dipole is a system with two opposite poles. Ordinary magnets are dipoles, but the word does not mean that they are made from two separate magnetic charges glued together. It describes the shape and orientation of their field. One side behaves as north, the other as south, and the field connects them in a continuous pattern. The microscopic sources inside the magnet are also dipolar. Electron magnetic moments behave like tiny magnetic dipoles. Atoms with unpaired electrons can carry dipole moments. Magnetic domains contain vast numbers of these atomic contributions aligned together. When a large dipole is built from smaller dipoles, cutting it separates groups of those smaller units. Each group still contains complete dipoles. The division never selects only the northern sides of the microscopic moments for one fragment and only the southern sides for the other. Every surviving atomic contribution continues to possess the paired field it had before. Picture a chain made from many tiny bar magnets placed end to end. The north end of one sits close to the south end of the next. In the middle of the chain, neighbouring poles partly cancel because they are pressed together. At the outer ends, one north and one south remain clearly exposed, so the full chain behaves like a single long magnet. Separate the chain between any two tiny magnets. One half now ends with the south pole of its final unit, while the other begins with the north pole of its first unit. Each half still contains complete miniature magnets, so each half has a complete pair of external poles. A real permanent magnet is not literally a stack of tiny bar magnets. Electron spin and quantum exchange make the underlying physics more subtle, yet the chain captures why no amount of ordinary cutting isolates one side of the magnetic behaviour. The building blocks are not single poles. There is also a more general rule hidden in the magnetic field itself. In every ordinary situation we have observed, magnetic field lines do not begin at a point and continue outward forever. They do not appear from nothing or disappear into nothing. They form closed paths. Outside a bar magnet, we describe the field as curving from north towards south. Inside the material, it continues back from south toward north. The complete path is a loop. That looping structure remains after the magnet is divided. Each fragment must still support complete loops. A line that appears to leave the north end eventually returns through the south end and the material. It cannot stop halfway in empty space. This is not because the field lines are physical ropes that must be tied together. Field lines are drawings used to represent direction, but their closed shape reflects a real property of the magnetic field. There is no confirmed isolated magnetic charge acting as a place where the field truly begins or ends. Electric fields are allowed to have such beginnings and endings because positive and negative electric charges exist separately. A proton carries positive electric charge. An electron carries negative electric charge. One can exist without the other sitting directly beside it. Electric field lines can spread outward from positive charge or converge toward negative charge. Magnetism appears different. Every known fundamental source in ordinary matter produces a dipole or a current-related field. There are no confirmed free north charges or free south charges. The field therefore loops. Physicists have a compact mathematical way of expressing this, but the idea can be said without equations. If you surround any ordinary magnet with an imaginary closed surface and measure how much magnetic field passes outward and inward, the totals balance. Whatever field leaves the enclosed region is matched by field returning into it. This remains true whether the imaginary surface surrounds the entire bar magnet, one fragment, a current-carrying coil, or a single atom with a magnetic moment. The field may be stronger in some places and weaker in others, but it does not produce an unmatched outward flow. Suppose we draw an imaginary balloon around the north end of a magnet but not the south end. Field lines seem to pass outward through much of that balloon, yet some also return through other parts because the field curves. The balance for a fully closed surface remains consistent with the absence of isolated magnetic charge. If a true magnetic monopole were trapped inside the balloon, the result would be different. The field could spread outward from a single north magnetic charge or inward toward a single south magnetic charge. No return pole would need to lie within the same object. That possibility is one reason magnetic monopoles fascinate physicists. They would not merely add another unusual particle to a list. They would change the basic source structure of magnetic fields. The closed-loop rule would need to be expanded to include magnetic charge. For ordinary magnets, however, the loop remains unbroken. A cut can reshape it, split one large pattern into two smaller ones, and create stronger local fields near the new surfaces, but it cannot produce a field with only a beginning and no return. The way magnetization meets a surface helps explain this more precisely. Inside the material, countless magnetic moments are aligned. In the middle of a uniformly magnetized bar, the neighboring contributions fit together. The north-like side of one microscopic dipole lies near the south-like side of the next. So much of their external influence cancels locally. At the end surface, the sequence stops. There is no next layer of magnetized material beyond the boundary to continue the cancellation. The exposed side therefore produces a stronger external pole effect. When the bar is cut, two new sequences stop at the cut faces. One fragment exposes one orientation, the other exposes the opposite orientation. This is why the fresh faces behave as opposite poles, even though nothing new has been inserted into the material. The effect is similar to cutting a tightly packed row of paired objects. Inside the row, neighbouring sides hide one another. At the ends, the unmatched surfaces remain visible. Make another cut and two more unmatched surfaces appear. The word unmatched must be used carefully. Each new surface may look like one kind of pole locally, but the fragment as a whole still has the opposite pole elsewhere. Nothing has become globally unmatched. This distinction between local and global behaviour matters. Near one end of a magnet, the field can look strongly north-like. A small compass or iron object responds mainly to that nearby region, but from a wider view, the South Pole and the return field are still part of the same system. The farther away you move, the more the two poles influence the field together. At great distances, the detailed shape of the magnet matters less, and the object behaves mainly as a dipole with a certain strength and direction. Cutting the magnet shortens the distance between each fragment's poles. It also reduces the amount of magnetized material in each piece. The field observed far away usually becomes weaker because each dipole is smaller. Close to the new surfaces, however, the field can remain strong. The local magnetization may be similar to what it was before the cut. This can create a surprising result in which a smaller piece still grips metal firmly near its pole, even though its overall field reaches a shorter distance. The fragments do not necessarily preserve perfect uniformity. Real magnets contain domains, defects, crystal grains, and internal stresses. When a new surface is created, the balance of magnetic energy changes. Some domains may turn, domain walls may move. The magnetization near the surface may curl into patterns that help the field return more efficiently. These changes can reduce the strength of the new poles or spread them unevenly across the cut face. The field still remains paired. Even a complicated domain structure cannot create a net isolated pole. It can create many small north-like and south-like regions on the surface, but when the full fragment is considered, the overall magnetic field forms complete loops. Imagine breaking a magnet into a rough, jagged piece. One corner may act strongly north-like. Another edge may show weaker south-like behavior. Small regions elsewhere may contribute in different directions. The pole map can become messy, rather like a compass trying to give directions inside a cupboard full of speakers. Yet if the entire field is measured, no unmatched pole remains. The complexity changes the distribution, not the fundamental pairing. The magnet's shape strongly influences where its poles appear. A long bar often concentrates pole behavior near its ends. A flat disc can be magnetized through its thickness, giving one circular face north and the other south. A ring magnet can have poles on its flat surfaces or around alternating sections of its circumference. Cut any of these shapes and the new fragments establish fields consistent with their remaining internal magnetization. A disc cut across its diameter may produce pieces with poles, arranged in ways that are less intuitive than those of a bar. A ring broken into arcs may produce strong pole regions at the fracture surfaces. The exact arrangement depends on the original magnetization direction and the geometry of the cut. The paired rule does not require every fragment to have one neat pole at each obvious physical end. It requires the complete magnetic field to contain both orientations and form continuous loops. Manufactured magnets can make this especially clear. Some are designed with many alternating north and south stripes across a single surface. Flexible refrigerator magnets often use this pattern. The close spacing of opposite poles concentrates the field near the surface that touches the refrigerator. If such a magnet is cut, each fragment may contain several north and south bands. It does not simply grow one new pole at each edge. Its existing pattern is interrupted, and the field adjusts around the new boundaries while preserving the overall balance. A compass moved across the surface may flip repeatedly as it passes from one band to another. The object contains many local pole regions, but they still come in connected arrangements. This tells us that the phrase "every fragment grows its own north and south pole" is a useful summary, not a complete map. The deeper statement is that every magnetized fragment forms a field with no isolated magnetic charge. Its magnetic order and boundaries produce both north-like and south-like regions. At extremely small scales, the fragment may become a single magnetic domain. Then its behavior can be simpler than that of a large multi-domain magnet. The entire particle has one dominant magnetization direction. Even a single domain particle remains a dipole. Its field has one orientation on one side and the opposite orientation on the other. It does not need separate internal domains to create two poles. Reduce the particle further and heat becomes increasingly important. Thermal motion may cause the magnetic direction to flip back and forth. Over a long measurement, the average field can appear to vanish. During any brief period when the particle points in one direction, however, its magnetic field is still dipolar. When it flips, north and south exchange sides together. One does not disappear while the other remains. At the level of an individual electron, the magnetic moment is also dipolar. There is no known smaller physical bar inside it that could be cut. Its magnetic property is part of its quantum identity. This creates a natural stopping point for the cutting idea. A magnet can be divided as a material object only while it remains a collection of atoms and particles. Eventually, cutting becomes breaking chemical bonds, separating atoms or changing the substance entirely. None of those ordinary processes reveals a hidden north charge. The known microscopic sources remain loops, spins, orbital motion, and dipole moments. The persistent pairing is therefore not a clever response invented by the fragment after it is broken. It reflects the kind of ingredients from which the magnetism was built. Complete dipoles produce complete dipoles at larger scales. This is similar to dividing a whirlpool-shaped pattern drawn across many tiles. Each smaller group of tiles may preserve part of the circulation or reorganize into a smaller complete pattern. You do not obtain a piece containing only clockwise motion with no return direction anywhere. There are limits to that comparison because magnetic fields are not fluids, and the microscopic physics is quantum mechanical. Still, circulation is a helpful idea. Magnetic effects are deeply connected to moving electric charge and angular momentum. Current travels in loops, and magnetic moments produce looping fields. Even in a coil of wire, the same principle is visible. Current passes around each turn, creating a magnetic field with north and south sides. Cut the wire, and the current stops unless a new complete circuit is made. You cannot retain half of a current loop and expect it to act as an isolated magnetic pole. A permanent magnet does not require a visible current travelling around its outer surface, but its magnetism is linked to electron motion and spin within matter. The resulting field has the same closed character. This is why cutting a magnet feels like asking the wrong question. The attempt assumes that north and south are two objects placed at opposite locations, but they are better understood as two aspects of an organised field. Asking where the north substance is stored is like asking where the upward part of a circle is stored. A circle has a top and a bottom because of its shape. Cut the circle and the pieces no longer form one complete circle. But if the physical system reorganises into smaller loops, each new loop again has a top and bottom. A magnetic field is not literally a circle drawn around the magnet, yet its continuous looping nature gives north and south their inseparable relationship. They are directions within one structure. The fragment does not create north from nothing. It reveals where the field now emerges relative to the surface. It does not create south from nothing. It reveals where the field now returns. If the fragment is turned around, the labels follow its magnetic orientation. What was the near side becomes the far side, but the internal field remains connected. If the magnetization is reversed by a strong external field, north becomes south and south becomes north together. That simultaneous reversal is another sign that the poles are not independent supplies. Changing the direction of the magnetic order changes both ends as one operation. There is no need to empty one pole and refill the other. The same idea explains why a magnet can lose its strong poles when heated or struck. If the domains become disordered, the shared orientation fades. The external north and south effects weaken together. The poles do not leave the object and travel away. The internal dipoles simply stop reinforcing one another. Their tiny fields point in many directions and cancel at larger scales. Magnetize the material again, and a strong pair returns. The process restores organized alignment, not a missing substance. By now, the refusal of a magnet to yield a single pole begins to look less like stubbornness and more like consistency. Every level of the ordinary magnetic system supports the same pattern. Electron moments are dipolar. A atomic moments are dipolar. Domains organise dipoles. The complete object produces a dipole field. Cutting divides the organisation, but does not change the nature of its sources. The remaining mystery is carried by the field itself. It reaches beyond the solid magnet, crosses empty space, turns compass needles, pulls iron, and loops back through the material. It can exist where there is no visible matter at all, storing energy and connecting distant objects without any physical cord between them. To understand why the poles always remain linked, we now have to follow those invisible loops more carefully, not only at the ends of the magnet but through the space around it, where the magnetic field reveals that north and south were never separate destinations in the first place. A magnetic field cannot be seen directly. It has no colour, no surface, and no edge that can be traced with a finger. It does not glow around a magnet like a faint mist, and it does not announce itself with a sound. Place a magnet alone on a table and the space around it looks perfectly ordinary. Dust settles as usual. Light crosses the room without hesitation. A cup of tea remains entirely unimpressed. Yet bring a compass, an iron nail, or another magnet nearby, and that apparently empty space suddenly reveals that something was there all along. The magnetic field is the part of the magnet that reaches beyond the solid material. It is how the magnet influences objects without touching them. The field surrounds the magnet, passes through the air, enters nearby materials, and continues through the magnet itself. It is not an extra coating placed around the outside. It belongs to the complete magnetic system. When iron filings are scattered over a sheet of paper resting above a bar magnet, the filings arrange themselves into curved bands. They gather most densely near the ends and form long arcs through the space around the magnet. The pattern looks almost like hair combed around an invisible shape. Each filing becomes temporarily magnetized and turns to line up with the local field. Together, they provide a rough map of something that cannot otherwise be seen. A compass can reveal the same field more carefully. Move a compass slowly around a bar magnet and the needle turns at every position. Near one end, it points away. Along the side, it swings into a curve. Near the other end, it points inward. If its direction is marked at many locations, the marks can be connected into looping paths. These paths are called magnetic field lines. They are useful drawings rather than physical objects. There are no actual cords stretched around a magnet, and nothing would become tangled if two fields overlapped. Field lines simply show the direction in which a tiny magnetic north pole would be pushed, if a free north pole could be used as a test. Since isolated magnetic poles have never been confirmed in ordinary experiments, the test pole is imaginary. A small compass provides the closest practical substitute. Its north-seeking end turns along the field, while the opposite end follows behind. By convention, field lines outside a bar magnet are drawn from the North Pole toward the South Pole. Inside the magnet, the direction continues from south back toward north. The full line closes into a loop. It does not stop at the South Pole, it passes through the material and returns. That return path is one of the central clues to why a magnet cannot be cut into separate poles. North and south are not places where magnetic and south are not places where magnetic lines truly begin and end. They are regions where the field passes between the material and the surrounding space. At the North Pole, the field points outward. At the South Pole, it points inward. Inside the magnet, the connection continues. If the bar is cut in half, the old field pattern cannot remain attached to an object that no longer exists as one piece. It reorganizes around the fragments. Each fragment contains internal magnetization, and each now has new surfaces. The field leaves one region, curves through the surrounding space, returns through another region, and continues inside the material. Two smaller loops replace one larger arrangement. The field does not need to ask which fragment deserves which part. Each piece already contains magnetic sources capable of producing a complete field. The reorganized loops appear because the matter and its magnetic order have been rearranged. It is tempting to imagine the field as something that pours from north and is absorbed by south. This can be a helpful picture at first, but it becomes misleading if taken literally. No magnetic liquid is flowing from one end to the other. The field is a physical condition spread through space. It tells us how magnetic forces would act at each location. Electric fields provide a familiar comparison. Place an electric charge in space and it changes the region around it. Another charge entering that region experiences a force. The electric field is the description of that influence. Magnetic fields work in a related way, but they act especially on moving electric charges and magnetic moments. A stationary compass needle contains many aligned magnetic moments, so it responds by turning. A moving charge can be deflected sideways by a magnetic field. A current-carrying wire can be pushed. Another magnet can rotate, attract, or repel. The field is not merely a mathematical convenience. It stores energy, carries momentum, and can transfer effects between objects. When two magnets attract, energy in the combined field changes as they move. When they snap together, some of that energy becomes motion, sound, and heat. The small click heard when they meet is partly the field rearranging the system into a lower energy state. Push matching poles together and the field resists the arrangement. Work must be done to hold them close. Release them and they move apart. The energy supplied by your hand was stored in the magnetic configuration and then returned as motion. Opposite poles behave differently because their fields connect more naturally through the gap. As they approach, the overall field can settle into a lower energy arrangement. The magnets accelerate toward one another, sometimes more eagerly than is comfortable for the fingers between them. The field also explains why iron is attracted to either pole. An ordinary iron object may not begin with a strong overall magnetic field because its domains point in different directions. Place it near a magnet and the external field encourages domains to align. The end closest to the magnet develops pole behavior opposite to the nearby pole. Attraction follows. If the north pole approaches an iron nail, the nearest end of the nail becomes south-like. If the south pole approaches, the nearest end becomes north-like. The nail rearranges its internal magnetization to suit the field, rather like a very accommodating guest who changes seats depending on who arrives. The attraction is strongest where the field changes most sharply. Near the ends of a bar magnet, the field is usually intense and uneven, so iron objects are pulled toward those regions. In a perfectly uniform field, a small magnet may rotate to align but experience little overall pull in one direction. A changing field produces the difference in force that moves it. This is why the shape of a magnet matters. A long bar spreads its field through a broad region. A horseshoe magnet bends the two poles close together, concentrating the field in the gap. Place an iron object across that gap, and the field can pass through the iron efficiently, producing a strong grip. The iron provides an easier path for the magnetic field than air. Magnetic materials respond to the field and guide much of it through themselves. This does not mean the field refuses to travel through air. It means the combined system stores less energy when the field follows certain materials. Engineers use this behavior in motors, generators, transformers, relays, and countless other devices. Iron cores guide magnetic fields through carefully chosen routes. Air gaps are placed where forces or energy storage are needed. Magnet shapes are selected to concentrate the field in useful locations. A loudspeaker contains a permanent magnet arranged to produce a strong field in a narrow gap. A coil of wire sits in that gap. When electric current changes direction through the coil, the magnetic force changes direction as well. The coil moves back and forth, pushing a cone that moves the air and creates sound. The invisible magnetic field becomes music, speech, or a reminder from a device that its battery is almost empty. The field itself remains unseen, but its work is everywhere. Electric motors use a similar principle. Currents in coils create magnetic fields that interact with permanent magnets or other electromagnets. The arrangement is designed so that attraction and repulsion produce rotation. The field turns electrical energy into motion. Generators reverse the process. Motion changes the magnetic arrangement near wires, producing electric current. Spin a coil in a magnetic field or move a magnet past a coil, and electricity can be generated. This connection was discovered through experiments showing that a changing magnetic field creates an electric field. A steady magnet sitting beside a wire does not necessarily produce current. Move the magnet, move the wire, or change the field, and electric charges in the conductor are pushed. The faster the magnetic environment changes, the stronger the induced electrical effect can become. Power stations rely on this principle. Turbines rotate coils and magnets, converting mechanical motion into electrical energy for homes, factories, and the occasional kettle that began this journey entirely unaware of its connection to electromagnetic theory. Electricity can also create magnetism. Send current through a straight wire, and a magnetic field circles around it. Bend the wire into a loop, and the field passes through the center of the loop. Wind many loops into a coil, and their fields reinforce one another, producing a pattern similar to that of a bar magnet. One end of the coil acts as north and the other as south. Reverse the current and the poles exchange places. The magnetic field forms closed loops around and through the coil, just as it does around a permanent magnet. This reveals a deep connection between loops of electric current and magnetic dipoles. A current loop produces a north and south pair. It cannot produce only one pole because the current itself circulates. The magnetic field follows the closed character of that circulation. The magnetism of atoms is not simply caused by tiny classical currents, because electron spin is a quantum property. Still, the resulting magnetic moments produce dipole fields with the same looping structure. At larger scales, the combined field of aligned moments resembles the field of current flowing around a coil. The field around Earth has a similar general shape. The planet behaves approximately like a giant magnetic dipole, with field lines passing through its interior and looping far into space. The field is produced by moving electrically conducting material in the liquid outer core rather than by a permanent bar hidden at the center. Heat escapes from deep within Earth, the planet rotates, and liquid metal flows. These motions generate electrical currents. The currents create magnetic fields, and the fields influence the flow in return. The result is a self-sustaining process known as a dynamo. Earth's magnetic field extends into a large region around the planet called the magnetosphere. It interacts with charged particles from the Sun and helps guide many of them around Earth. Near the polar regions, some particles enter the upper atmosphere and produce auroras. The coloured lights of an aurora are not magnetic field lines becoming visible. They come from atoms and molecules in the atmosphere emitting light after being struck by charged particles. Yet the magnetic field guides those particles, shaping where the display appears. The field around a simple magnet is far smaller, but the principle is related. Charged particles do not need to touch the magnet to respond. They move through a region where the electromagnetic conditions influence their paths. A magnetic field does not usually push a moving charge directly along the field direction. Instead, the force acts sideways relative to the motion. This can bend a particle into a curve or a spiral. Charged particles entering Earth's field can therefore spiral around field lines while also travelling along them. In particle accelerators, powerful magnets bend fast moving particles around circular tracks. Other magnets focus beams so they do not spread apart. The magnetic field is doing no simple pulling toward north or south. It is shaping motion according to the direction of the charge in the field. Magnetism becomes less like an invisible rope and more like a rule built into space that tells moving charges how to turn. The field is also relative to the observer. Electricity and magnetism are not fully separate phenomena. An observer moving with respect to charges may describe the situation differently from someone at rest. What appears mostly electric in one frame can include magnetic effects in another. Relativity shows that electric and magnetic fields are parts of one electromagnetic field. They can transform into one another depending on motion. This does not mean a refrigerator magnet stops being magnetic when someone walks past it. It means the deeper description unites electricity and magnetism into one structure. Light itself is an electromagnetic wave. A changing electric field produces a changing magnetic field, and the pair travels through space. Radio waves, microwaves, visible light, ultraviolet radiation, and other forms of electromagnetic radiation differ mainly in frequency and wavelength. The light crossing the room therefore contains magnetic fields as well as electric fields. They oscillate rapidly and move together through space. The magnetic part of an ordinary light wave is not strong enough to make spoons leap from a table, but it belongs to the same electromagnetic framework as the field around a bar magnet. This connection gives the invisible loops around matter a much broader setting. Magnetism is not an isolated curiosity found only in iron and compass needles. It is one expression of a field that also gives us electricity, radio, light, chemistry, and much of modern technology. Yet the field of a permanent magnet has a special stillness. It can remain present without visibly changing. The magnet may sit untouched for years while its field continues through the surrounding space. Where does the energy come from to maintain it? The magnet does not continually burn fuel. A static magnetic field does not require a constant supply of energy merely to exist. The energy is part of the organized state of the material in its field. Creating the magnet required work. Domains were aligned, materials were processed, and the system was placed into a particular magnetic state. Once that state is stable, it can persist without continuously spending energy. The magnet can perform work when its configuration changes. Let it pull an iron object closer, and stored magnetic energy decreases while motion increases. To repeat the action, the object must be pulled away again, restoring energy to the system. The magnet is not an endless energy source. It is more like a spring that can pull only after someone has stretched the arrangement. This is why two magnets cannot be used to power a machine forever without an external input. Attraction can produce motion once, but separating the magnets requires energy. A carefully built motor uses changing electric currents to keep rearranging the fields and maintain rotation. The electricity provides the continuing energy. The shape of the field also changes with distance. Close to a magnet details matter. The exact pole shape, surface texture, domain arrangement, and material influence the field. Far away, those details blur together, and the magnet behaves mainly like a simple dipole. The field weakens rapidly with distance. A strong magnet may lift an object when close but have little effect across a room. This is fortunate because otherwise every filing cabinet, speaker, and fridge magnet would be engaged in a constant and exhausting disagreement. When two magnets are far apart, their fields overlap weakly. Bring them closer, and the overlap becomes stronger. The total field at any point is the combination of both contributions. Fields can add or partly cancel. Between opposite poles, they often reinforce in a connected direction. Between matching poles, they point against one another in some regions, producing a point where the total field may be small. Iron filings near matching poles bend away from the central region, showing that the fields resist joining directly. Near opposite poles, the filings form dense bridges across the gap. These pictures make magnetic attraction and repulsion appear almost mechanical, but the field is not a substance under pressure in the ordinary sense. It is a physical entity described by values at every point in space. The shape of those values determines forces and energy. Modern physics goes further and treats the electromagnetic field as quantum mechanical. At the deepest level, interactions between charged particles are described through the quantum electromagnetic field. Light comes in particles called photons, which are excitations of that field. A static magnetic field is not best imagined as a cloud of ordinary visible photons flying between poles. The full quantum description is more subtle. Still, the classical field used in engineering and everyday magnetism emerges from that deeper quantum framework. The field therefore belongs both to the large world of motors and compasses and to the small world of particles and quantum states. It connects the motion of electrons inside a magnet with forces acting centimeters or meters away. Most importantly for our original question, the field preserves the partnership between north and south. Every ordinary source creates a field with continuous loops. When matter is divided, those loops reorganize. They do not become loose lines with one end abandoned in space. A fragment may have a complicated surface. It may contain many domains. Its field may twist and close over short distances. But wherever one region behaves north-like, another part of the complete system provides the south-like return. To break this rule would require something not found inside an ordinary permanent magnet. It would require a genuine source or destination for magnetic field, an isolated magnetic charge that could exist without an opposite pole attached. Physics has a name for such an object. It is called a magnetic monopole. Some theories suggest that monopoles should exist. Others suggest they may have been created in the early universe. Experiments have searched for them in rocks, cosmic particles, accelerators, and sensitive detectors. The invisible loops around familiar magnets tell us why finding one would matter so much. A monopole would not merely be another stronger magnet or a strange piece of metal. It would allow a magnetic field to begin or end in a way ordinary matter never does, opening the possibility that north and south might finally exist apart. For everything we have seen so far, north and south behave like inseparable partners. Break a magnet and both appear again. Grind the fragments into smaller pieces and the pairing survives. Move down through domains, atoms and electrons, and the magnetic sources still behave like dipoles, with one orientation on one side and the opposite orientation on the other. The field curves outward, loops through space, and returns. Nature seems determined to prevent a magnetic pole from wandering off alone, but physicists have never been entirely satisfied with that rule. If positive and negative electric charges can exist separately, why should magnetic north and magnetic south always remain attached? An electron can carry negative electric charge without a proton sitting beside it. A proton can carry positive charge without an electron permanently glued to its surface. Electric charge comes in individual units. A magnetic pole, by contrast, appears only as part of a pair. This difference has bothered scientists for a very long time. It makes the laws of electricity and magnetism look almost symmetrical, but not quite. The equations describe electric and magnetic fields in closely related ways. Changing electric fields can create magnetic fields. Changing magnetic fields can create electric fields. Light carries both together through space. Yet one part of the partnership has isolated charges, while the other seems to have none. A magnetic monopole would repair that imbalance. The word monopole means one pole. A magnetic monopole would be an object that carried magnetic charge without an opposite pole attached. One type would behave like a north pole on its own. The other would behave like a south pole on its own. Its magnetic field would not need to curve back through the same object. It could spread outward or inward in a way resembling the electric field around an isolated charge. This would not be the same as cutting a very small permanent magnet. A tiny magnet is still a dipole. It has both north and south in its field, even if the object is too small to see. A true monopole would be fundamentally different. It would not contain a hidden opposite pole waiting at the far side. It would carry an unmatched magnetic charge. If you placed a north monopole near the north end of a bar magnet, it would be repelled. Near the south end, it would be attracted. Move it away, and it would remain a north monopole. It would not need to bring a south pole along for the journey. That sounds simple enough, but no confirmed fundamental magnetic monopole has ever become part of established experimental physics. Scientists have searched for them in space, in rocks, in particle detectors, and in powerful collisions. The search has lasted for decades, and so far, nature has not offered an unmistakable specimen. The idea gained serious attention through the work of the British physicist Paul Dirac. Dirac was one of the founders of quantum mechanics and had a remarkable habit of following mathematics into places where new particles seemed to be hiding. His work on the electron helped predict antimatter before the positron was discovered. In the early 1930s, Dirac asked what would happen if even one magnetic monopole existed somewhere in the universe. He found something extraordinary. The existence of a monopole could explain why electric charge comes in fixed units. Electric charge is quantized. Every free electron carries exactly the same amount of negative charge. Protons carry an equal amount of positive charge. Other particles can carry related values, but the charges are not found in arbitrary amounts. You do not discover one electron with a slightly stronger charge because it had a productive morning. The values arrive in precise steps. Physics describes this fact very accurately, but explaining why charge must come in those steps is more difficult. Dirac showed that if a magnetic monopole existed, the rules of quantum mechanics would force electric charge to be quantized. The relationship was striking. A single monopole anywhere in the universe could impose a rule on every electrically charged particle. As Dirac famously observed in Essence, the beauty of the idea made monopoles worth taking seriously even though none had been seen. The reasoning involves the quantum behavior of charged particles moving through magnetic fields. A charged particle is described by a wave-like state. When it travels around a monopole, the state must return consistently to itself. That requirement links electric charge and magnetic charge in exact amounts. We do not need the mathematical details to appreciate the result. The monopole would provide a reason that electric charges come in uniform units rather than random values. It would connect two facts that otherwise appear unrelated. This turned the magnetic monopole from a curious possibility into something that could explain a real feature of nature. Physicists began wondering whether monopoles might not only be allowed but necessary. Later developments made them seem even harder to avoid. During the 1970s, physicists explored theories that tried to unite the electromagnetic force with a strong nuclear force. These are known as grand unified theories. The Standard Model describes the electromagnetic, weak, and strong forces with remarkable success. Yet it treats them through different structures. Grand unified theories propose that at extremely high energies, these forces were once aspects of one larger force. The early universe would have reached such energy shortly after the beginning of cosmic expansion. As the universe cooled, the unified force may have separated into the forces we observe today. This process is sometimes compared with water freezing, although the comparison is only approximate. The physical state changes, and a more symmetrical arrangement becomes a less symmetrical one. When certain grand unified theories undergo this kind of change, magnetic monopoles appear naturally. They emerge as stable structures within the fields, rather like knots or twists that cannot easily be removed. These monopoles would not necessarily be elementary particles in the simplest sense. They could be extended field configurations built from the unified forces themselves. Even so, they would behave as particles with magnetic charge. The theoretical work of Gerardus de Hooft and Alexander Polyakov showed that monopole solutions appeared in broad classes of unified theories. This was important because the monopole no longer depended only on placing one into the equations by hand. In these theories, it arose as a natural consequence. That created a new problem. If grand unified monopoles were produced in the early universe, there should have been an enormous number of them. They would be very massive, extremely stable, and difficult to destroy. The universe, however, does not appear to be filled with magnetic monopoles. If large numbers were present, they would affect cosmic evolution, matter, radiation, and the magnetic fields of galaxies. We would expect detectors occasionally to encounter one. This became known as the monopole problem. theories predicted too many monopoles, while observations found none. Cosmic inflation offered a possible solution. Inflation is the idea that the early universe experienced a brief period of extremely rapid expansion. During that expansion, any monopoles created beforehand could have been spread so far apart that only a tiny number remained within the region we can observe. Imagine placing a few grains of sand on the surface of a balloon, and then expanding the balloon to an enormous size. The grains do not disappear, but the distance between them becomes vast. A small observer on one part of the balloon might never encounter one. Inflation could therefore explain why monopoles are rare without requiring them to be impossible. Perhaps a few still travel through the universe, separated by distances so great that finding one would require extraordinary patience and good fortune. This possibility has inspired searches in cosmic rays. A monopole moving through space could pass through Earth and interact with matter in distinctive ways. Because it would carry magnetic charge, it might ionize atoms, leave unusual tracks, or produce electrical signals in sensitive equipment. Some detectors are placed underground to reduce interference from ordinary cosmic particles. Others use large volumes of material and wait for something unusual to pass through. A monopole might be extremely rare, so detectors must watch for long periods while rejecting countless ordinary events. One method uses loops made from superconducting material. A magnetic monopole passing through such a loop would change the magnetic flux in a permanent and characteristic way. The loop would retain a change in current after the monopole had passed. An ordinary magnetic dipole entering and leaving the loop would not produce the same lasting signal. Its north and south contributions would balance. A monopole could leave a net step, almost like a single magnetic footprint. Scientists have also searched ancient rocks and minerals. If monopoles existed in cosmic rays, some might have become trapped in matter during the history of Earth. Samples can be passed through sensitive measuring devices to look for persistent magnetic charge. Meteorites are another possible place to search. They contain material that has travelled through space for extremely long periods and may have encountered conditions different from those on Earth. Lunar samples have also attracted interest because the Moon lacks the same geological recycling that continually reshapes Earth's surface. Particle accelerators provide another route. High-energy collisions recreate on a tiny scale some of the extreme conditions of the early universe. If monopoles can be produced at accessible energies, collisions might create them in pairs. A north magnetic charge and a south magnetic charge would likely be produced together so that the total magnetic charge remains balanced. The two could then move apart, becoming genuine isolated monopoles rather than opposite ends of one ordinary magnet. Because a monopole would interact very strongly with electromagnetic fields, it might lose energy rapidly while passing through detector material. It could leave an unusually intense trail of ionization. Some experiments use layers of plastic that preserve damage tracks left by highly ionizing particles. Other searches include special trapping materials placed near collision points. A monopole produced in a collision might slow down and become caught inside. The material can later be scanned with highly sensitive magnetic instruments. These experiments are difficult because no one knows exactly how massive a monopole would be. Different theories predict different properties. A grand unified monopole could be far too massive for any human-built accelerator to produce. Lighter monopoles might exist in other models, but their expected behaviour varies. Scientists therefore search across wide ranges of possible mass, speed, and magnetic charge. A detector designed for a fast monopole from a cosmic ray may not be ideal for a slow, heavy monopole trapped in rock. A collider experiment may be sensitive to one theoretical type but not another. There have been occasional events that caused excitement. A detector records an unusual signal. A piece of material appears to carry a strange magnetic response. For a moment, the possibility of discovery enters the room. But extraordinary discoveries require repeated evidence. A genuine monopole should be examined by independent teams, detected in more than one way, and shown not to be an instrumental error or ordinary magnetic contamination. So far, no candidate has survived that process strongly enough to become accepted. The absence of a discovery still teaches physicists something. Every unsuccessful search rules out part of the possible range. It places limits on how common monopoles can be, how strongly they interact, or how easily they can be produced. A detector that watches for years without seeing one can show that fewer than a certain number pass through a given area over that time. A collider that produces billions of collisions without a signal can rule out some monopole masses or production rates. This is how science often advances when the object being studied remains hidden. Not finding something does not prove that it exists nowhere. It narrows the places where it can hide. The search becomes even more interesting because objects described as magnetic monopoles have been created in certain materials. These are not fundamental monopoles, but they imitate some of the expected behaviour. One important example comes from materials called spin ices. In these materials, magnetic moments are arranged in a crystal structure that creates frustration. Frustration in physics does not mean the atoms are irritated, although the arrangement gives them good reason to be. It means that local interactions cannot all be satisfied at once. Imagine several people trying to sit around a small table while following rules that require each person to face away from one neighbour and toward another. The geometry may make it impossible for everyone to satisfy every rule. The system settles into one of many compromises. In spin ice, the magnetic moments often follow a local pattern, described informally as two pointing inward and two pointing outward around small structural units. If one magnetic moment flips, it creates two defects in that pattern. Those defects can move apart through further flips. One behaves as though it carries north magnetic charge, and the other behaves as though it carries south magnetic charge. They can become separated by many atomic distances. From within the material, they look remarkably like monopoles. Magnetic field patterns appear to begin near one defect and end near the other. The two defects can move independently through the crystal. Yet they are not fundamental free monopoles. Their existence depends on the surrounding material, their collective excitations produced by the coordinated behaviour of many magnetic moments. A useful comparison is a hole moving through a row of seats. Suppose every seat is occupied except one. As people move one place at a time, the empty seat appears to travel down the row. The hole behaves like a moving object, even though it is really a pattern of many people shifting. In a semiconductor, a missing electron can also behave like a positively charged particle called a hole. The hole is not a tiny object made from positive material. It is an absence that moves through the electron system and responds as if it carries charge. The monopole-like defects in spin ice work in a related way. They behave as magnetic charges within the material, but they cannot be removed from that environment and carried through empty space as fundamental particles. Other experiments have created monopole-like structures in ultra-cold atomic gases and specially designed magnetic systems. Scientists can shape quantum states so that the surrounding field resembles the field of a monopole. These achievements are valuable. They allow researchers to study how monopole-like objects move, interact, and emerge from collective behaviour. They also show that the mathematics of monopoles can appear naturally in physical systems. But they do not answer the original fundamental question. They do not provide a lone north magnetic charge that could be placed in a container and taken away from the laboratory. There are also objects called monopoles in certain gauge theories and quantum systems that behave differently from the grand unified particles imagined in cosmology. The word is used in several related settings, which can create confusion. A headline may announce that scientists created a magnetic monopole, while the experiment actually produced an analog or an emergent excitation. That does not make the achievement unimportant. An artificial whirlpool is still useful for studying circulation, even if it is not a hurricane. The distinction simply matters when asking whether nature contains fundamental magnetic charge. A true monopole would have consequences far beyond magnetism. It could help explain charge quantization. It might reveal that the known forces unite at high energies. It could preserve information about the early universe. Its mass and structure might point toward physics beyond the standard model. It could also change the way we write the laws of electromagnetism. The familiar equations would become more symmetrical. Electric charge and magnetic charge would appear side by side. Electric currents and magnetic currents would have matching roles. That symmetry is deeply appealing. Physicists often take symmetry seriously because it has repeatedly guided successful theories. Yet beauty alone does not make a particle real. Nature is allowed to be less tidy than our preferences. There is another unusual feature of magnetic charge. If a monopole carried the smallest amount allowed by Dirac's condition, its magnetic interaction would be very strong. This makes calculations difficult. Many ordinary particle theories rely on interactions being weak enough for physicists to approximate them in a series of manageable steps. For monopoles, that familiar approach may fail. Their strong coupling means that predicting how readily they would be produced in a collider is uncertain. Experiments can search for them, but translating a missing signal into a precise statement about theory can be complicated. A monopole might also bind strongly to ordinary matter. Once captured, it could remain trapped in atomic nuclei or magnetic materials. It might catalyze unusual processes in some theories, possibly encouraging protons to decay. Experiments have looked for these effects as another indirect sign. None has produced a confirmed discovery. The continued absence may mean monopoles are extraordinarily rare. It may mean they are too massive for current experiments. It may mean inflation diluted them almost completely. It may mean the relevant theories do not describe nature. Or it may mean that magnetic monopoles do not exist at all. Physics does not yet know which answer is correct. This uncertainty is part of what makes the subject so useful. The missing pole sits at the meeting point of several major questions. Why is the electric charge quantized? Did the forces of nature once form a single interaction? What happened during the earliest moments of the universe? Which particles remain beyond the standard model? A small bar magnet leads unexpectedly into all of them. If a fundamental monopole were discovered, it would not mean that cutting a household magnet suddenly became a method for separating poles. The magnet would still be made from electron moments and domains. Its north and south ends would still be features of a dipole field. A monopole would be a new ingredient, not a hidden piece of the old one. It would resemble the difference between finding an electron and cutting a charged plastic rod. The rod's charge comes from an imbalance of electrons, but slicing the rod is not how the electron itself was discovered. In the same way, the poles of a bar magnet are not monopoles glued together. They arise from aligned dipoles. A true monopole would need to be found as a particle, a stable field structure, or some other fundamental source of magnetic charge. Even if monopoles existed, they might be difficult to use. A single one could have an enormous mass. It could interact strongly with materials and become trapped. Creating or controlling it might require energies far beyond current technology. There is therefore no immediate prospect of placing north monopoles in one box and south monopoles in another, then using them to build a magnetic device with only one pole. The search is driven by the desire to understand nature, not by a plan for a monopole-powered refrigerator door. Still, imagine what a confirmed signal would mean. A detector records a permanent step exactly matching magnetic charge. Another laboratory finds the same effect. A trapped object is moved through repeated tests and behaves as a monopole every time. The closed loops around ordinary magnets would no longer be the entire story. Magnetic field lines could have genuine sources and endings. The apparent asymmetry between electricity and magnetism would be reduced. A prediction reaching back through decades of theory would finally have a physical object attached to it. Until then, every magnet we cut continues to answer in the same way. North appears with south, south appears with north. The fragments reproduce the dipole pattern because the material contains only the known magnetic building blocks. The missing monopole remains missing, but its absence has shaped physics almost as strongly as a discovery might have done. It encouraged new theories, inspired detectors, influenced ideas about cosmic inflation, and revealed strange forms of magnetic behavior inside matter. Sometimes a question becomes powerful not because nature answers it quickly, but because every failed answer points towards something deeper. Why can we not isolate a pole? Perhaps the universe contains monopoles but hides them at unreachable energies. Perhaps it created them and then scattered them across impossible distances. Perhaps the laws allow them mathematically while the history of our universe produced almost none. Or perhaps the paired structure of ordinary magnetism is telling us that the familiar north and south are not objects at all. They are directions within a field, two sides of a relationship created by motion, spin, and the organization of matter. That possibility brings us back from the early universe to the magnet in your hand. The missing pole does more than create a search for a hypothetical particle. It forces us to ask what a magnetic pole really is, what counts as fundamental, and what the refusal of a magnet to split reveals about the way nature builds large visible effects from invisible quantum rules. A magnet that refuses to surrender a single pole may seem like a small laboratory curiosity. It is the sort of fact that can be demonstrated in a classroom with a brittle bar magnet, a marker, and a little confidence about where the fragments will land. Cut the object in half, test the pieces, and each one has north and south again. The experiment takes only a moment. The explanation, however, reaches through the structure of matter, the nature of fields, the rules of quantum mechanics, and the unanswered questions of particle physics. What looks like an unbreakable pair is really a lesson about how the universe builds large things from small patterns. The north and south poles of an ordinary magnet are not separate objects placed at opposite ends. They are visible features of a continuous magnetic arrangement. That arrangement begins with electrons, spreads through atoms, becomes organized across domains, and finally produces a field large enough to move a compass needle or lift a paperclip. The two poles remain together because the known microscopic sources of ordinary magnetism are themselves dipolar. Electron spin gives an electron a magnetic moment. Orbital motion can add another contribution. Atoms combine those effects. Neighbouring atoms influence one another through quantum interactions. Domains gather vast numbers of magnetic moments into shared directions. At every stage, the magnetic field has two sides. It points outward relative to one region and inward relative to another. It curves through space and returns through the material. Dividing the object changes the size and shape of the pattern, but it does not change the kind of pattern being divided. This is one of the most useful habits physics teaches. When an object behaves strangely, the problem may lie not in the object but in the picture we have chosen for it. If we imagine a magnet as a container with north material stored at one end and south material stored at the other, cutting should separate them. The experiment then seems mysterious. Once we imagine the poles as consequences of an organized field, the result becomes more natural. A cut creates new surfaces. The internal magnetization reaches those surfaces and new pole regions appear. Nothing grows from nothing. Nothing crosses the fragment to repair a missing end. The boundary changes, so the visible field changes with it. The same lesson appears in many parts of science. Temperature is not a substance hidden inside a hot object. It emerges from the motion and energy of countless particles. Sound is not a material carried inside a bell. It is a pattern of vibration moving through matter. A wave is not a separate object sitting on top of the water. It is organized motion spreading across the surface. Magnetic poles belong to this family of ideas. They are real, measurable, and capable of producing force, but they are not necessarily fundamental objects. They emerge from a deeper organization. Emergence is one of the quiet wonders of physics. A single water molecule is not wet. One air molecule does not possess a breeze. An individual atom does not have the hardness of steel or the softness of wax. Those properties appear when enormous numbers of particles interact. A magnet follows the same principle. One electron has a magnetic moment, but it cannot hold a note to a refrigerator. One atom may contribute magnetism, but it does not create the field of a motor. A permanent magnet becomes possible only when an immense population of quantum objects settles into a coordinated state. The strength in your hand comes from cooperation at a scale too small to see. Countless electrons contribute tiny effects. Many cancel, some remain. In the right material, quantum exchange encourages neighbouring moments to align. Domains form. Enough domains point together, and the weak microscopic contributions become a powerful macroscopic field. The process is not merely a larger version of tiny classical magnets stacking together. Quantum mechanics determines which electrons can share states, how their spins combine, and why certain materials favour parallel or opposing alignment. The permanent magnet is therefore a large object whose behaviour depends on rules that have no perfect everyday equivalent. That fact makes a magnet an unusually accessible piece of quantum physics. We often imagine quantum effects as delicate phenomena confined to cold laboratories, microscopic particles, or experiments that require equipment with an alarming number of cables. Yet a magnet works because quantum properties remain organised across ordinary matter at ordinary temperatures. Pick up a magnet and you are holding a stable collective quantum state. It may be coated in plastic and decorated like a fruit, but the underlying physics has not become less impressive. The magnet also reveals how much of reality exists beyond direct sight. Its field is invisible, yet it has direction, strength, energy, and measurable effects throughout the surrounding space. A compass turns before touching the magnet. An iron object accelerates across a gap. A wire carrying current experiences a force. The empty space between the objects is not playing no role. It contains the magnetic field. Fields change the way physicists understood forces. In an older picture, one object seemed to act directly on another across empty space. The sun pulled Earth. A charged object attracted another charge. A magnet moved a compass needle. The connection was described through the force, but what occupied the distance between them remained unclear. The field picture assigns physical properties to every location in space. The magnet establishes a magnetic field around itself. Another magnetic object responds to the field where it happens to be. The interaction is local in the sense that the object responds to the conditions immediately around it. This view became central to electromagnetism and later to modern physics as a whole. Fields are no longer treated as optional drawings placed over reality. In quantum theory, fields are among the most fundamental ingredients we know. Particles themselves can be understood as excitations of fields. The electron is associated with an electron field. Light is an excitation of the electromagnetic field. Other particles arise from other fields. What appears to us as solid matter is a stable organisation of quantum fields interacting. The magnetic field around a bar magnet is therefore part of a much larger idea. Reality may be built less like a collection of tiny marbles and more like a set of fields capable of producing particles, forces, waves, and organised states. The looping magnetic field also reveals an important distinction between local appearance and complete structure. Stand near the north end of a magnet and the region behaves strongly north-like. From that limited viewpoint, it may seem as though only one pole matters. Step back and map the full field. The south pole and the return path become unavoidable. What looked like a one-sided effect was part of a larger connected system. Nature often hides completeness beyond the scale of our immediate view. A small patch of a wave may look like simple upward motion, but the full wave includes rise and fall. One section of an orbit may resemble motion in a straight line, but the full path curves. A local region of the universe may look flat even if the larger geometry is not. The magnet warns us not to confuse the part we can see with the whole structure producing it. This lesson becomes especially clear when the object is cut. The attempt to isolate a pole focuses on location. North is here, south is there. Separate the locations and the poles should separate as well. But the poles are not defined only by location. They are defined by relationship and orientation. One is north only because the magnetic field has a certain direction relative to the other side. Change the orientation of the magnet and the label's exchange places. Reverse the internal magnetization, and both poles reverse together. North and south are not permanent identities attached to particular atoms. The atoms at the original north end could become part of the south end after remagnetization. The matter remains while the role changes. This suggests a broader point about scientific categories. Many names describe what something does within a system, rather than what it is by itself. A cause and an effect depend on order. A sender and receiver depend on communication. An entrance and exit depend on how a space is used. North and south depend on the orientation of a magnetic field. The poles are relational properties. Each helps define the other. That does not make them imaginary. Relationships can be physically real. The distance between two objects is real, even though it does not belong to either object alone. The angle between two lines is measurable, even though it is not stored inside one line. A magnetic pole is real as a region within a field pattern, even if it is not a separate substance. The inseparability of the poles also connects magnetism with conservation laws. Physics is filled with quantities that cannot simply appear or disappear without accounting. Energy changes form but is conserved. Electric charge is conserved. Momentum passes between objects and fields. For ordinary magnetism, the balance between outward and inward magnetic field is always preserved. Surround a magnet with an imaginary closed surface, and the total magnetic field passing outward is balanced by the field passing inward. No net magnetic charge is enclosed. Cut the magnet and draw separate imaginary surfaces around the fragments. The same balance holds for each piece. One fragment cannot produce only outward magnetic field because its internal sources do not allow it. Another cannot absorb magnetic field without returning it. The field lines form loops because there is no confirmed fundamental magnetic charge acting as a beginning or ending. This absence makes electricity and magnetism strangely unequal. Electric charges exist independently. Electrons and protons can be separated. Electric field lines can begin and end on charge. Magnetic fields in the familiar world have no equivalent isolated sources. The missing magnetic monopole therefore reminds us that the laws of nature may contain symmetries that are hidden, incomplete, or broken by the conditions of our universe. The equations of electromagnetism would look beautifully balanced if magnetic charges existed beside electric charges. Perhaps they do exist, and are simply rare. Perhaps they were produced in the early universe and scattered beyond reach by cosmic inflation. Perhaps they are so massive that no human accelerator can create them. Perhaps only certain deeper theories contain them, and those theories do not describe our universe. The continuing search is valuable because any of these answers would teach us something important. Finding a monopole could explain why electric charge comes in fixed units. It could support theories that unite the forces of nature. It could provide a surviving relic from the earliest moments after the universe began expanding and cooling. Failing to find one also matters. Each search narrows the possibilities. Each empty detector places limits on how common monopoles can be. Each collider result tells physicists which masses and interactions remain possible. Science does not advance only through objects placed proudly on laboratory tables. It also advances by learning when nature refuses to cooperate. There is a gentle irony in the monopole search. Scientists want to find the one thing that an ordinary magnet can never provide. They break magnets, examine particles, watch cosmic rays, scan ancient matter, and create monopole-like behavior inside specially arranged materials. Nature repeatedly offers imitations, patterns, and theoretical hints, but no confirmed isolated magnetic pole. The absence keeps the question alive. The paired nature of ordinary magnetism also reveals the importance of topology, the study of properties that depend on continuity in connected structure. A loop is different from a line with two free ends. You can bend or stretch a loop without changing the fact that it closes. To open it, you must break the continuity. Magnetic field lines around ordinary sources behave as closed loops. Cutting the material changes the field configuration, but it does not turn the field into open lines because the underlying source structure remains unchanged. The new fragments generate new closed patterns. Certain theoretical monopoles appear as topological structures in fields. Their stability would come not from being made of an indestructible material, but from the way the field is arranged. Removing them might require changing the entire structure rather than simply breaking an object. This is another place where everyday intuition becomes unreliable. We tend to think stability means hardness or strong bonds. In field theory, something can be stable because its pattern cannot be smoothly untied. A knot in a rope is not a different material from the rope, it is an arrangement. Yet the knot can behave like an object with a position and motion. In some theories, particles and monopoles can resemble knots, twists, or defects in fields. The magnet in your hand does not contain these grand unified monopoles, but its behavior prepares the mind for the possibility that patterns can be as physically important as substances. The same idea appears in vortices, waves, crystal defects, and quasi-particles. A whirlpool can travel even though the water molecules forming it are continually replaced. A sound wave moves through air without carrying the same air across the room. A missing electron in a material can behave like a positively charged particle. Physics repeatedly finds object-like behavior emerging from organized relationships. North and south are another example. They seem like two objects, but they are parts of one field structure. The effort to cut them apart fails because the structure is reproduced in each fragment. There is also a lesson about scale. At the human scale, a magnet is a solid bar with two ends. At the microscopic scale, it is a landscape of domains. Within each domain are atoms. Within the atoms are electrons whose quantum states determine magnetic moments. At a deeper level, those electrons are excitations of quantum fields. Each scale offers a different explanation, and none is completely replaced by the one below it. An engineer designing a motor can work with magnetic fields and pole arrangements without calculating every electron. A materials scientist studies domains and crystal structures. A particle physicist asks whether monopoles exist. A quantum theorist examines spin and exchange interactions. All are describing the same broad phenomenon at different levels. This layered understanding is one reason science can feel both satisfying and unfinished. We can explain why cutting a magnet creates two magnets with great confidence. We can describe domains, electron spin, and field loops. We can build machines that use magnetism with extraordinary precision. Yet the explanation opens questions that remain unresolved. Why does nature contain electric charge but no confirmed magnetic charge? Why are the forces arranged as they are? Did magnetism look different at the enormous energies of the early universe? Are monopoles waiting beyond the reach of present experiments? A complete answer at one level becomes a doorway at another. That is not a failure of knowledge. It is how knowledge grows. The fact that a simple question leads toward deeper questions does not make the simple answer less true. It shows that nature is connected. The magnet on the table is linked to the quantum rules inside electrons. Those rules are linked to the structure of matter. The field around the magnet belongs to electromagnetism. Electromagnetism belongs to the wider framework of particle physics. The missing monopole may belong to the history of the universe itself. A child asking why the poles cannot be separated has quietly pointed toward grand unification and cosmology. Physics has a habit of hiding very large doors behind very small questions. There is something else the magnet reveals. The universe does not always permit us to isolate every concept we name. We can speak about north and south separately. We can label them, test them, and describe their different effects. But naming two aspects does not guarantee that nature allows them to exist independently. We name the crest and trough of a wave, but neither makes a complete wave alone. We speak of action and reaction, but they belong to one interaction. We separate space and time in conversation, yet relativity joins them into space-time. Our language divides ideas for convenience. Nature may keep them connected. This does not mean every apparent pair is fundamentally inseparable. Positive and negative electric charge can be separated. Matter and antimatter can exist apart. Different systems follow different rules. The point is that experiments, not intuition, decide which distinctions correspond to independent physical objects. With magnets, the experiment has answered consistently. Cut once, and there are 2 pairs. Cut again, and there are 4. Continue until the material no longer behaves like the original solid, and the microscopic magnetic moments remain dipolar. The refusal is not symbolic, it is physical evidence about the sources of magnetism. Perhaps one day a detector will record a true magnetic monopole. Then physicists will learn that north and south can exist separately under conditions far removed from a household magnet. The discovery would expand the story rather than erase it. Ordinary magnets would still contain aligned dipoles. Cutting them would still produce smaller magnets. Their poles would still emerge from boundaries and field orientation. A fundamental monopole would simply reveal that nature has another form of magnetic source, one that familiar matter does not usually contain. Until such a discovery, every broken magnet gives the same quiet demonstration. The original north end remains on one fragment. A new south appears at the cut. The original south remains on the other. A new north faces it across the gap. Push the pieces together and the fresh poles attract. Pull them apart and each fragment carries its own field. Turn one piece around and the interaction changes. The entire puzzle can be held between 2 fingers. What looked at first like a failed attempt to divide an object becomes a clear view of organization. The magnet is not a container of poles, it is a pattern of magnetic order. The poles are where that pattern meets the world. That idea reaches beyond magnetism. Many things we experience as objects may be stable patterns. Matter is built from fields. Particles are defined by properties and interactions. Solids are held together by quantum rules. The familiar world emerges from arrangements too small and strange for everyday intuition. A magnet makes that hidden structure unusually easy to feel. Its field pushes back through empty space. Its poles reverse without changing the shape of the object. Its domains remember previous fields. Its electrons cooperate across the material, and whenever it is divided, the same complete pattern returns. So the answer to why you cannot cut a magnet in half is both simple and deep. You can cut the material, you can shorten the bar, you can create fragments. What you cannot do through ordinary cutting is separate north from south, because they were never independent pieces inside the magnet. They are the 2 sides of one magnetic field, created by organized dipoles throughout the material. Each cut makes new boundaries. Each boundary reveals the orientation already present. Every fragment, therefore, becomes another complete magnet. Somewhere nearby, perhaps on a refrigerator door or hidden inside a speaker, a magnet may be doing this without attracting any attention. Its electrons remain aligned. Its field forms invisible loops. Its north and south poles stay together, not because they're tied by a tiny thread, but because they are expressions of one continuous physical structure. And if you found this quiet journey through magnetism soothing, interesting, or useful, you might leave a like and subscribe to Physics with William. It helps these slow explorations reach other curious listeners who may enjoy discovering how much of the universe can be hidden inside an ordinary object. For now, there is no need to search for a saw or begin testing every magnet in the house. It is enough to know that the small object holding up a note is also holding together a lesson about quantum mechanics, fields, symmetry, and the way nature turns invisible organization into something we can feel. North remains with south. The field leaves and returns. The pieces become smaller, but the relationship survives. And in that unbreakable pair, the universe offers one more reminder that the deepest parts of reality are often not separate things, but patterns that only make sense together.